The universe's largest structure, the Great Attractor, the invisible pull. You are moving right now, even as you sit perfectly still. Not just spinning with Earth or circling the Sunday. You, the Sun, every planet, and every star in the Milky Way are all being drawn through the cosmos at roughly 600 kilometers per second. That's over 2 million kilometers every hour, fast enough to cross the distance between Earth and the Moon in under 7 minutes. And yet, this motion isn't toward any nearby galaxy or cluster. It's aimed at a mysterious point deep in the southern sky, toward the constellations Centaurus and Norma, where something enormous lies hidden behind the Milky Way's blinding heart. Astronomers call it the Great Attractor, a gravitational anomaly so massive that it bends the motion of entire galaxy clusters across hundreds of millions of light years. For decades, it has stood as one of the most intriguing riddles in cosmology, a place that can't be seen directly, yet exerts a measurable, undeniable pull on our entire corner of the universe. The story begins not with what we see, but with what shouldn't be happening. When astronomers first mapped galaxies in the mid-20th century, they noticed something peculiar. Most galaxies appear to recede from us, their light stretched to longer, redder wavelengths by the expansion of the universe. The farther away a galaxy is, the faster it should appear to move. This is Hubble's law, the foundation of cosmology. But by the late 1970s, new data revealed that not all galaxies followed this neat, predictable trend. Some were drifting off course, showing peculiar velocities, extra motions superimposed on the universal expansion. These galaxies weren't just receding because the cosmos was stretching. They were also sliding sideways, as though pulled by something massive yet unseen. At first, the deviations seemed minor anomalies buried in noise. But when astronomers combined data from hundreds of galaxies, a pattern emerged. A broad, coherent flow of galaxies, all moving in roughly the same direction, toward a region hidden behind the dense clouds of the Milky Way's central band. This wasn't a few galaxies taking a shortcut through space, it was an entire supercluster complex of galaxies, including our own local group, moving toward an invisible gravitational basin. To understand how strange this is, imagine the universe as a vast, expanding ocean. Galaxies drift apart like buoys carried by the current of cosmic expansion. Now imagine noticing that an entire patch of the ocean, hundreds of buoys over hundreds of millions of light years, appears to be drifting slightly faster in one direction. Something must be disturbing the flow, creating a hidden undertow in space-time itself. For the Milky Way, that undertow pointed directly toward Centaurus. Early measurements suggested that our local group of galaxies, including the Milky Way, Andromeda, and dozens of smaller companions, was streaming at about 600 kilometers per second toward this hidden region. To put that in perspective, that's nearly twice the orbital speed of Earth around the Sun, and several times faster than the escape velocity from the Milky Way's center. But what could produce such a gravitational pull, one strong enough to influence not just nearby galaxies, but entire superclusters spread across hundreds of millions of light years? The first clues came from surveys conducted in the 1970s. Teams measuring galactic redshifts noticed systematic deviations from the Hubble flow, especially in the direction of the Hydra and Centaurus constellations. The data implied a mass concentration beyond the visible limits of known clusters. Yet the same direction coincided with the most difficult part of the sky to observe: the zone of avoidance, a region obscured by the Milky Way's dense disk of dust, gas, and stars. It was as if the universe had hidden its largest secret directly behind the bright glare of our own galaxy. The zone of avoidance blocks visible light from billions of stars and galaxies. Dust clouds in the galactic plane absorb and scatter most optical wavelengths, leaving astronomers effectively blind to what lies beyond. Only radio and infrared waves can penetrate this curtain. But in the late 1970s, infrared astronomy was in its infancy, and radio maps were too coarse to reveal fine detail. The result? An enormous gravitational influence with no visible cause. By the early 1980s, the evidence was impossible to ignore. Galaxies over a vast region of sky stretching from the Virgo cluster all the way to Hydra Centaurus showed coordinated motion toward a single gravitational sink. The phenomenon didn't fit any known local structure. Even after accounting for the Virgo supercluster's pull, the excess velocity remained. Something immense was out there, tens of thousands of galaxies worth of mass, hidden behind our own. In 1986, a group of astronomers, led by Donald Lynden Bell, Alan Dressler, and Sandra Faber, a team that came to be known as the Seven Samurai, quantified this motion for the first time. Their analysis of galaxy peculiar velocities showed that the entire local group and much of the nearby cosmic neighborhood were moving toward a point roughly 150 to 250 million light-years away, in the direction of the Centaurus and Norma constellations. They called this mysterious destination the Great Attractor. But at that moment, it was a name without an image, an empty place on the map that warped the trajectories of galaxies as if by magic. The team's calculations suggested that the Great Attractor contained the mass equivalent of tens of thousands of galaxies, concentrated across a region roughly 40 to 50 million light-years wide. That's about the size of the Virgo supercluster, yet its gravitational influence extended far beyond. Even galaxies not physically part of it seemed to feel its pull. From our vantage point, the Great Attractor sits close to the galactic plane, near galactic longitude 307 degrees, latitude 9 degrees, where interstellar dust and stars are densest. If you pointed a regular telescope there, you'd see nothing but the Milky Way's luminous haze. Yet behind that glow lies a gravitational field, reshaping the motion of hundreds of thousands of galaxies. This realization changed how astronomers viewed the cosmic neighborhood. The universe was not a random scatter of galaxies. It was a structured web of matter, with vast filaments and clusters linked by gravity. The Great Attractor marked one of the deepest gravitational wells in that web, a place where matter had collected over billions of years, sculpted by dark matter's invisible hand. Still, one question lingered. What exactly is it? Even now, nearly half a century after its discovery, the Great Attractor is not a single object. It's a region, a complex of overlapping galaxy clusters and dark matter concentrations located in the direction of the Norma cluster, Abell 3627, and the Centaurus cluster. Together, these structures anchor the Hydra Centaurus supercluster, a vast concentration of mass near the heart of what astronomers now call the Laniakea supercluster, our cosmic home. Observations from X-ray and radio telescopes have since revealed that the Norma cluster alone contains thousands of galaxies and emits intense X-rays from its hot intracluster gas, heated to tens of millions of degrees Kelvin. Such temperatures correspond to tremendous gravitational potential consistent with the pull first inferred by the Seven Samurai. And yet, the Great Attractor is not the end of the story. Beyond it lies the even larger Shapley concentration, nearly 650 million light-years away, a supercluster so massive it may ultimately dominate our galaxy's long-term trajectory. When you look up at the night sky, you see light that has travelled for millions of years. But in that time, the Milky Way has already moved millions of light-years closer to the Great Attractor, drawn by gravity's faint but relentless tug. Every star, planet, and molecule you know is part of that motion. You are not fixed. you are falling slowly, gracefully, into a deeper gravitational sea. The Great Attractor reminds us that even the universe's largest scales are not static. Galaxies are not isolated islands. They are part of an immense cosmic current, shaped by structures so vast they bend the flow of entire superclusters. What we perceive as stillness is motion on a scale too large for human senses to detect. Somewhere beyond the Milky Way's shimmering band, beyond the veil of dust and starlight, an invisible concentration of mass is pulling us across the universe. And though we cannot see it, we can trace its influence in the motion of everything around us, a whisper of gravity that speaks across hundreds of millions of light years. The universe, it seems, is not just expanding outward, it is also drawing inward toward unseen anchors that shape its grand design, discovery and the seven samurai. By the mid-1970, astronomy had entered an age of precision. The cosmic expansion discovered by Edwin Hubble was well established, and for the first time, large catalogues of galactic redshifts were being compiled. The idea seemed simple. The farther away a galaxy is, the faster it should recede from us. Yet, as data poured in, astronomers noticed tiny deviations, hundreds of kilometers per second, faster or slower than Hubble's law predicted. At first, these oddities were brushed aside as local quirks. A cluster's internal motions here, a miscalibrated distance there. But by the end of the decade, the pattern grew impossible to ignore. Across swathes of the southern sky, galaxies appeared to share the same peculiar motion, as though the entire region, Virgo, Hydra, Centaurus, and even our own local group was sliding together toward one hidden direction. The universe, it seemed, had a subtle asymmetry, an invisible hand pulling on everything nearby. The need for a new kind of map. To make sense of the anomaly, astronomers needed not just redshifts, but true three-dimensional distances. Measuring them was the hardest challenge in extragalactic astronomy. The most reliable method for spiral galaxies came from a discovery by R. Brent Tully and J. Richard Fisher. A galaxy's intrinsic brightness correlates with how fast it rotates. Brighter spirals spin faster. By observing the width of a galaxy's 21 centimeter hydrogen line to a measure of its rotation, they could estimate its actual luminosity. Comparing that to its apparent brightness gave the distance. The relation, soon called the Tully-Fisher relation, became the cosmic ruler of the 1970. But to use it effectively, astronomers needed large, uniform samples, precise photometry, and careful correction for inclination, dust, and internal absorption. It was a perfect task for a dedicated team willing to invest years in collecting and cleaning data. Enter the Seven Samurai. In 1983, 7 astronomers joined forces across 5 institutions: Alan Dressler, Sandra Faber, Donald Lyndon Bell, Roger Davies, David Burstein, Roberto Turlevich, and Gary Wegner. They called their informal collaboration the Seven Samurai, a nod to Kurosawa's film about a small band achieving the impossible. Their goal was nothing less than to chart the motion of galaxies within 100 million parsecs, about 325 million light-years, and uncover the source of their unexplained drift. Each member brought expertise: Faber's mastery of galaxy dynamics, Lyndon Bell's deep intuition for gravitational flows, Dressler's meticulous observation skills. Together they compiled redshift and distance data for hundreds of galaxies, most drawn from the revised Shapley-Ames catalogue and newly measured 21 centimeter line widths. The data were processed through custom statistical models that corrected for observational bias and local group motion. What they found stunned them. When they subtracted Hubble expansion from each galaxy's velocity, a clear pattern emerged. Almost all the galaxies in their survey shared a residual motion of roughly 600 kilometers per second toward a point in the sky near galactic longitude 307 degrees. Latitude +9 degrees deep in the constellations Centaurus and Norma. The motion wasn't local. It spanned regions tens of millions of light-years apart. Something enormous, far beyond the Virgo cluster, was drawing them in. The birth of a name. In 1986, the team published their results in Astrophysical Journal under the modest title Spectroscopy and Photometry of Elliptical Galaxies, v. Galaxy streaming toward the new supergalactic center. Inside, however, lay a revolution. The paper proposed the existence of a gravitational concentration containing 10 to the power of 16 solar masses, hundreds of times the mass of Virgo, centered roughly 200 million light-years away. It needed a name. In discussion notes and seminars, Lyndon Bell jokingly referred to it as the Great Attractor, and the nickname stuck. The term captured both its mystery and its audacity. A hidden region powerful enough to bend the trajectories of entire superclusters. Skepticism arrived instantly. How could such an enormous structure have escaped detection? Many argued that the team's velocity field might simply be an artifact of poor distance calibration. Others pointed out that the supposed direction coincided with the most obscured part of the Milky Way, the zone of avoidance, where visible light surveys were blind. The microwave conformation, the Seven Samurais hypothesis, received dramatic support from an entirely different corner of physics. In 1965, the discovery of the cosmic microwave background, CMB, had provided a frame of reference for cosmic motion. Any motion relative to this background should create a tiny temperature difference across the sky, a dipole anisotropy through the Doppler effect. In 1977, measurements from balloon experiments, and later the COBE satellite in 1989, detected exactly that. The CMB appeared slightly warmer in the direction of Centaurus and cooler in the opposite direction. The implied velocity was 627 ± 22 kilometers per second, aimed squarely toward the same coordinates identified by the Seven Samurai. The coincidence was overwhelming. Two independent methods, galactic velocity mapping and microwave background measurements, agreed not only in speed but in direction. The Milky Way, the Virgo cluster, and hundreds of neighboring galaxies were indeed plunging toward an unseen gravitational basin, looking into the dark. Still, what was there? The 1,980 lacked the infrared and X-ray satellites needed to peer through the Milky Way's dust. Astronomers turned to radio telescopes like the Parkes 64-metre dish in Australia. Radio waves at 21 centimetres pass unimpeded through interstellar dust, revealing the neutral hydrogen clouds of distant galaxies. By the late 1980s, radio surveys began to pick up hints of massive clusters near the coordinates of the supposed attractor. Among the first was the Norma cluster Abell, 3,627, a rich assembly of galaxies about 220 million light-years away, embedded in the Hydra Centaurus region. Later, X-ray satellites such as HEAO-1 and ROSAT confirmed intense emissions from hot intracluster gas, a signature of immense gravitational confinement. The pieces were falling into place. The Great Attractor corresponded not to a single object, but to an extended region dominated by the Norma and Centaurus clusters, bound together in a massive supercluster complex. Recharting the cosmic neighborhood, the Seven Samurais analysis did more than name a mystery. It redefined cosmic geography. Before 1986, the Virgo supercluster was thought to be the dominant structure of our local universe. with the Milky Way lying comfortably within its boundaries. The new velocity field showed otherwise. The local group's motion could not be explained by Virgo's gravity alone. The attractor's influence stretched far beyond, pulling on Virgo itself. Later surveys by Alan Dressler and collaborators in 1988 used data from the IRAS, infrared astronomical satellite, to trace galaxy densities outside the obscured zone. The results supported the Seven Samurais model. The mass over density extended across more than 40 megaparsecs, centered near Hydra Centaurus. By the early 1990s, consensus grew that the Great Attractor represented the central node of a vast Hydra Centaurus supercluster, itself one of the dominant features within what would decades later be recognized as the Laniakea supercluster, our true cosmic continent. A shift in cosmological thinking. The impact of the discovery was profound. Astronomers realized that the universe's large-scale structure wasn't random. Galaxies were arranged in filaments, sheets, and nodes formed by gravity acting on dark matter over billions of years. The Great Attractor was one of those nodes, a deep gravitational well sculpted by both visible and invisible matter. It also exposed the sheer scale of dark matter's influence. The luminous galaxies visible in the attractor region account for only about 10% of the mass required to generate the observed velocities. The rest must reside in dark matter halos and intracluster gas. The Seven Samurai had stumbled not just upon a structure, but upon an experiment in cosmological mass accounting evidence that most of the universe's matter is unseen. The human element. Behind the data lay years of debate and persistence. Each new data release forced the group to re-examine their calibrations, to defend against critics who claimed the effect might vanish with improved distances. Faber later recalled that they felt like detectives chasing a ghost, rechecking every assumption, every formula. Their collaboration spanned continents and time zones, maintained by phone calls and hand-mailed tapes of data long before email became common. Their perseverance paid off. Within a decade, nearly every major redshift survey, IRAS, ESO, and later 2DF, confirmed large-scale flows consistent with the Great Attractor's pull. By the time Brent Tully and Hélène Courtois produced their 2014 map of Laniakea, the Great Attractor had evolved from an anomaly to a central landmark in cosmic cartography. The broader consequences. Understanding this motion also refined our place in the universe. The 600 km per second velocity towards Centaurus adds vectorially to Earth's 30 km per second orbit around the Sun, and the Sun's 220 km per second orbit around the galactic center. Our true motion through the cosmos is a complex sum of nested rotations and drifts, ultimately directed toward the Great Attractor's gravitational basin. The dipole pattern in the CMB, the warm, cool asymmetry in the sky, is the echo of that cosmic voyage. In a sense, the Seven Samurai didn't just find a structure, they measured the heartbeat of our galactic neighborhood, the rhythm by which matter moves through the cosmic web, toward the hidden realm. Even as evidence mounted, the Great Attractor remained largely unseen. The Milky Way's dust still blocked the direct view. To map it clearly would require instruments capable of piercing the galactic plane with infrared and X-ray vision technologies that were only beginning to emerge. Astronomers were preparing a new generation of surveys to lift the veil. COBE, Spitzer, 2MASS, Chandra, and XMM Newton. These would finally reveal the anatomy of the structure that the Seven Samurai had inferred only from motion. But the deeper the observations went, the more complex the picture became. Beyond the Great Attractor lay yet another concentration of mass, the Shapley concentration, nearly 3 times farther away and potentially even more massive. The Great Attractor once thought to be the ultimate destination, might be only a midpoint in a larger gravitational cascade stretching across 500 million light-years. The Seven Samurais' discovery marked a turning point in cosmology. It connected the local universe to the global tapestry of structure formation, linking our modest galaxy to a chain of superclusters bound together by invisible gravity. Their work demonstrated that the cosmos is not static but dynamic, a web of motion, tension, and flow. Today, when you look toward the southern Milky Way, hidden behind the bright stars of Centaurus, you are looking into the same direction they plotted almost 40 years ago. Behind that glow lies the gravitational heart of our region of space, the Great Attractor first revealed not through sight, but through the faint, collective motion of galaxies drifting toward it, mapping the monster. If the Great Attractor were a creature, it would be one made not of flesh or flame, but of gravity, an immense distortion in the fabric of space-time itself. It doesn't roar or blaze, it simply pulls. Its existence can only be inferred through the behavior of galaxies that fall toward it, as if caught in a slow, silent whirlpool millions of light-years across. Now that astronomers could finally see through the Milky Way's fog, the task shifted from detection to dissection. What is the Great Attractor made of? How massive is it? How far does it stretch? And what exactly gives it such overwhelming gravitational power? Locating the heart. By the late 1990s, with the combined power of radio, infrared, and X-ray astronomy, the coordinates of the Great Attractor had been narrowed to a region centered around galactic longitude 307 degrees, latitude plus 9 degrees deep in the direction of the Norma and Centaurus constellations. The core of its mass lay roughly 150–250 million light-years from Earth, or about 4570 megaparsecs. The centerpiece of this hidden domain turned out to be the Norma cluster Abell 3627, a massive assembly of galaxies located at a redshift of Z is approximately equal to 0.016, corresponding to about 220 million light-years. It sits almost exactly behind the densest part of the Milky Way's disk, making it almost invisible in optical light. Yet when viewed through infrared and X-ray eyes, it becomes one of the most spectacular nearby clusters in the universe. The Norma cluster contains roughly 5,000 galaxies packed into a region 10 million light-years across. Its total gravitational mass is estimated to be around 1 × 10 to the power of 15 solar masses, or about 1,000 Milky Ways worth of material. But its true significance lies in its environment. Norma doesn't sit alone. It anchors a vast web of clusters and filaments, connecting to Centaurus, Pavo, and Hydra, forming the backbone of the Hydra-Centaurus supercluster, the visible manifestation of the Great Attractor's gravitational basin. The X-ray skeleton. X-ray astronomy revealed that the Norma cluster glows intensely in high-energy light. Its intracluster gas is heated to temperatures of around 6 × 10 to the power of 7 K, 60 million Kelvin, hot enough to emit copious X-rays detected by ROSAT, Chandra, and XMM Newton. The X-ray brightness peaks sharply toward the center, where the gravitational potential is deepest. This emission comes from ionized plasma gas, so hot that electrons and nuclei move freely, colliding and producing radiation known as thermal bremsstrahlung. By measuring the X-ray brightness profile, astronomers can infer the mass distribution of the cluster. In the case of Norma, the data indicate that visible matter, stars, and gas makes up only a small fraction, less than 15% of the cluster's total mass. The rest must be dark matter, forming a dense, invisible halo that dominates the gravitational potential. The X-ray structure of Norma also shows shock fronts and asymmetries, evidence that the cluster is still merging with smaller groups. This suggests that the Great Attractor region is dynamically active, a growing hub where gravity continues to collect matter along filamentary channels of the cosmic web, filaments and flow. When infrared surveys, like 2MASS and WISE, mapped galaxies across the zone of avoidance, they revealed an extraordinary network. The Great Attractor region is not a spherical blob of galaxies, it's a filamentary complex, shaped like a spider's web of light and gravity. One major filament stretches from the Centaurus cluster about 160 million light-years away down through the Norma cluster and continues toward the Pavo-Indus Telescopium supercluster chain, which itself extends another 100 million light-years. These filaments act as cosmic highways, funneling galaxies and dark matter into the Great Attractor's gravitational core. Along them, galaxies move not randomly, but coherently, each one tracing a slow, graceful descent toward the region's deep potential well. Astronomers describe these collective trajectories as peculiar velocity vectors superimposed on the universe's overall expansion. Instead of moving straight outward with the Hubble flow, galaxies within this region appear to drift sideways, curved slightly toward the Great Attractor's center. In three-dimensional velocity maps, the motion resembles water spiraling down a vast cosmic drain. Our own Milky Way sits on one of the outer ripples, caught in the gravitational tide, measuring the mass. How massive is this drain? Estimating the Great Attractor's total mass has been a challenge since its discovery. The original Seven Samurai analysis suggested an overdensity of around 10 to the power of 16 solar masses, though that number came with large uncertainty. Subsequent mapping refined the estimate, showing that the combined Hydra-Centaurus-Norma region likely contains 510 times 10 to the power of 15 solar masses of matter, roughly 100,000 times the mass of the Milky Way. This mass is distributed across an enormous volume, roughly 50-70 million light-years in diameter. Within that span, galaxy density is about 5 times higher than the cosmic average. The gravitational potential created by such a structure is easily strong enough to accelerate our entire local group toward it at roughly 600 kilometers per second, as measured through the cosmic microwave background dipole. To visualize that number, at 600 kilometers per second, the Milky Way moves 1.5 million kilometers every hour toward the Great Attractor. Over the course of a year, we drift 5 billion kilometers closer, roughly the distance between the Sun and Pluto. And yet, at that speed, it would still take more than 100 billion years to reach the Great Attractor, longer than the universe has existed. The pull is not about destination, it's about direction. It defines our motion through the local universe, shaping how galaxies cluster, merge, and evolve. Comparing giants. For scale, the Virgo cluster, our nearest major neighbor, contains about 1,300 galaxies and a total mass of roughly 10 to the power of 14 solar masses. The Coma cluster, farther away, is even larger, with about 4 times 10 to the power of 14 solar masses. But both pale in comparison to the Great Attractor region, where multiple clusters Norma, Centaurus, Hydra, and Pavo combine to create a gravitational entity at least 10 times more massive than Virgo. In X-rays and infrared, this mass distribution looks less like a single cluster and more like an overlapping chain of gravitational basins, each feeding into the next. The Norma cluster appears to serve as the main hub, while Centaurus and Hydra form lateral anchors. The entire complex resembles a gravitational continent embedded within a network of filaments stretching hundreds of millions of light-years. Dynamics of attraction. So, how does the Great Attractor exert its influence across such enormous distances? The answer lies in the gravitational potential field. It generates an invisible landscape of valleys and ridges in space-time. When cosmologists model galaxy motion, they account for both the Hubble expansion, the universe's general stretching, and the local gravitational perturbations superimposed on it. Galaxies fall toward overdense regions while avoiding underdense ones, voids. In the case of the Great Attractor, the overdensity creates a local infall region extending at least 100 million light-years from its core. Within this region, the flow of galaxies deviates significantly from pure expansion. The velocities of galaxies in Hydra, Centaurus, and even Virgo all tilt inward toward the same attractor basin. Simulations suggest that the gravitational acceleration induced by the Great Attractor contributes roughly 15% of the Milky Way's total peculiar velocity, with the rest arising from the cumulative pull of the larger Laniakea supercluster and the distant Shapley concentration. The picture that emerges is dynamic, not static, a continual migration of matter through cosmic filaments, flowing like rivers into gravitational seas. The role of dark matter. The Great Attractor is as much a triumph of dark matter physics as it is of observation. The luminous galaxies and hot gas we can see account for only a fraction of its mass. The rest must exist as dark matter, which interacts gravitationally but not electromagnetically, making it invisible to every telescope. Numerical simulations of structure formation, such as those from the Millennium Simulation Project, show that massive superclusters like Hydra Centaurus form where long filaments of dark matter intersect. Over billions of years, gravity amplifies these intersections, pulling in normal matter to create clusters and galaxies along the dark scaffolding. In this view, the Great Attractor represents one of the densest dark matter nodes in our cosmic neighborhood, a place where invisible mass has shaped the motion of visible matter for over 10 billion years. Its gravitational well likely extends far beyond the boundaries of the Norma cluster itself, blending seamlessly into the larger basin of the Laniakea supercluster, discovered in 2014 by R. Brent Tully and Hélène Courtois. In that sense, the Great Attractor may be less a separate object and more the central eddy within a much greater cosmic current, mapping in motion. Modern efforts to map the monster no longer rely on static pictures but on velocity field reconstructions, mathematical models that use galaxy motions to infer the underlying gravitational potential. In 2014, Tully and Courtois used data from over 8,000 galaxies with measured peculiar velocities to create a three-dimensional flow map of the local universe. The result was breathtaking. All major galaxies within 160 megaparsecs were shown to be streaming toward a single basin, centered near the Hydra Centaurus region, the Great Attractor, while galaxies beyond that ridge flowed toward the Shapley concentration even farther out. This visualization provided the most compelling confirmation yet. The Great Attractor is the gravitational core of Laniakea, our home supercluster. In this map, the Milky Way's motion is not an isolated drift, but part of a coherent pattern. We, Virgo, Hydra, Centaurus, and Norma all belong to one immense gravitational river system, a cosmic watershed whose currents extend hundreds of millions of light-years. The monster's reach. The gravitational reach of the Great Attractor extends well beyond its visible structure. Galaxies, as far as 300 million light-years away, show measurable infall toward its direction. Even the motion of the local group, our Milky Way Andromeda and their companions is oriented along this vector. In numbers, the local velocity field can be broken down as to 300 kilometers per second toward Virgo, to 200 kilometers per second toward the Great Attractor, Hydra Centaurus, to 100 kilometers per second influenced by more distant structures like Shapley. Together, they sum to the 600 kilometers per second motion measured relative to the cosmic microwave background. That single number, 600 kilometers per second, encapsulates everything: the combined gravity of all nearby overdensities, the depth of the Great Attractor's potential well, and the dynamic structure of the local universe. The living structure. The Great Attractor is not static. Clusters within it are still merging, colliding, and heating the surrounding plasma. The Norma cluster itself shows X-ray and radio evidence of active galactic nuclei, merger shocks, and turbulent flows, signs that the structure is dynamically evolving. Over billions of years, smaller clusters will continue to fall inward along filaments, deepening the gravitational well. Eventually, the Great Attractor and its surrounding clusters may merge into a single, massive supercluster core, though cosmic acceleration driven by dark energy will slow and eventually halt large-scale infall. For now, the region stands as a snapshot of cosmic evolution in progress, a gravitational metropolis still under construction. The human perspective. When we say the Milky Way is moving toward the Great Attractor, it's easy to imagine some distant destination, a point we will one day reach. But in reality, the motion is part of an ongoing gravitational ballet, an oscillation within the web of space-time. The Great Attractor defines our direction of fall, not our fate. It is a reminder that the universe, even on scales of hundreds of millions of light years, is still sculpted by gravity's slow, inevitable dance. Every galaxy we see is moving not randomly, but along pathways carved by ancient mass concentrations, rivers of motion that tell us where the invisible matter lies. The Great Attractor has gone from an unseen anomaly to a charted landscape of clusters, filaments, and hot plasma. A living structure whose gravity sculpts the motion of galaxies across vast cosmic expanses. Yet, as immense as it is not the end of the story. Beyond it, farther still, lies something even greater. A supercluster so massive it dwarfs even Hydra Centaurus and pulls on our galaxy from hundreds of millions of light years farther away. To map that is to step beyond the Great Attractor itself into the deeper gravitational sea of the cosmos, the cosmic web connection. If the Great Attractor is a whirlpool of gravity, then the sea it churns within is the cosmic web, an intricate, three-dimensional tapestry of matter stretching across the observable universe. To understand the Great Attractor fully, one must see it not as an isolated anomaly, but as a node within this vast web, a gravitational knot where filaments of galaxies converge, binding our cosmic neighborhood together. Every galaxy you've ever seen, every star, cluster, and nebula lies on one of these invisible threads. The spaces between them are not empty, but vast voids spanning hundreds of millions of light years, where matter is scarce and gravity's pull is weak. Between those voids, gravity has drawn the universe into a filamentary network, like frost patterns on glass, connecting galaxies across unimaginable distances. The Great Attractor is one of those intersections, a gravitational nexus near the heart of the local web. From chaos to structure. After the Big Bang, matter in the universe was almost perfectly uniform, with density fluctuations of only 1 part in 100,000. The first evidence of this came from the cosmic microwave background, mapped in exquisite detail by Kobe, 1989, WMAP 2001, and Planck 2013. These tiny ripples, mere temperature differences of microkelvins, were the seeds from which every structure in the cosmos would grow. Over billions of years, gravity amplified those ripples. Regions slightly denser than average pulled in more matter, forming filaments, walls, and nodes, while less dense regions became voids. By the time the universe reached its current age of 13.8 billion years, these structures had evolved into a vast cosmic web spanning the entire observable universe. Computer simulations, such as the Millennium Simulation 2005 and Illustris TNG 2018, show how this process unfolds. The universe looks less like a random scatter of galaxies and more like a neural network, bright filaments of galaxies converging on dense hubs. Within each hub, matter condenses into clusters and superclusters, the largest coherent structures in the cosmos. The Hydra Centaurus supercluster, which contains the Great Attractor, is one such hub, a node in the cosmic web, connected by filaments that stretch hundreds of millions of light years in every direction. A supercluster named Laniakea. For decades, astronomers described our cosmic neighborhood in terms of familiar landmarks: the local group, home to the Milky Way and Andromeda; the Virgo supercluster, a region about 110 million light-years across; and, farther afield, the Hydra Centaurus supercluster, thought to be an adjacent structure. But in 2014, astronomers R. Brent Tully, Hélène Courtois, Yehuda Hoffman, and Daniel Pomered redefined this map entirely. Using peculiar velocity data from over 8,000 galaxies, they created a three-dimensional model of galactic motion. What they found changed the way we understand cosmic geography. The Virgo supercluster, it turned out, wasn't an isolated island at all. It was part of a much larger gravitational continent. The new map showed that our galaxy, along with Virgo, Hydra, Centaurus, and Norma, all occupy a single vast structure spanning 520 million light-years and containing over 100,000 galaxies. They named it Laniakea, a Hawaiian word meaning immense heaven. In their model, galaxies within Laniakea move coherently toward a single gravitational basin, the Great Attractor. Beyond that basin, galaxies flow outward toward another, even deeper one, the Shapley concentration. The boundary of Laniakea is defined by the points where these flows diverge, much like the ridgelines separating watersheds on Earth. The Great Attractor, then, is not just a destination, it is the heart of Laniakea, the gravitational low point toward which everything in our local universe drifts. A universe of filaments and voids. Laniakea is just one of many superclusters woven into the cosmic web. Imagine standing in intergalactic space and looking out across billions of light-years. You would see a glowing network of filaments connecting bright knots of clusters separated by immense black voids. Among these vast structures are the Perseus-Pisces supercluster, stretching over 300 million light-years, a long filament of galaxies visible from the northern hemisphere. The Coma Wall, anchored by the Coma Cluster, one of the densest regions known. The Sloan Great Wall, discovered in 2003, extends over 1.4 billion light-years, containing thousands of clusters. The Hercules Corona Borealis Great Wall, discovered in 2013, possibly the largest structure in the observable universe, a filament over 10 billion light-years long. Compared to these cosmic giants, Laniakea may seem modest, but to us, it is home. It contains every galaxy whose gravity affects ours within a radius of 250 million light-years. It defines our local gravitational environment, and the Great Attractor is its beating heart. How the cosmic web shapes motion. The Great Attractor's influence is not simply a pull, it is part of a gravitational flow field shaped by surrounding voids and filaments. The local void, a vast, underdense region adjacent to the local group, pushes our galaxy outward while the Great Attractor pulls inward. Together, they define the vector of our cosmic motion. In cosmology, this interplay between attraction and repulsion is modeled using velocity field reconstructions. Galaxies move along gradients of gravitational potential toward overdensities, away from underdensities. The dipole-repeller hypothesis, proposed by Yehuda Hoffman and colleagues in 2017, suggests that part of our galaxy's motion comes not only from being pulled toward the Great Attractor and Shapley concentration, but also from being pushed away by large voids like the local void and the Delphinus void. Thus, the Milky Way's 600 km per second velocity is the result of a cosmic tug-of-war gravity pulling from one side, emptiness pushing from the other. The dark scaffolding. At the foundation of this cosmic web lies dark matter, the invisible material that constitutes about 85% of all matter in the universe. It neither emits nor absorbs light, but its gravity dictates where galaxies form. Simulations show that dark matter forms a scaffolding of filaments and nodes long before normal matter condenses into stars and galaxies. Hydrogen gas follows these invisible threads, cooling and collapsing where dark matter density peaks. The Great Attractor region corresponds to one of these dark matter nodes, a thick intersection of filaments linking the Hydra, Centaurus, Norma, and Parvo clusters. The mass-to-light ratio here is extraordinarily high, indicating vast quantities of dark matter. X-ray data from Chandra and XMM Newton show that the baryonic normal matter accounts for only about 15% of the region's total mass. The rest is unseen. In this sense, the Great Attractor is more than a gravitational curiosity. It's a window into dark matter's architecture, an observable manifestation of an invisible framework that governs the universe's shape, a cosmic continuum. Seen within this context, the Great Attractor is not an isolated mass concentration, but a transitional zone, a gravitational gateway connecting our part of the universe to the deeper structures beyond. At one end lies the local sheet, the flattened region containing the Milky Way and its neighbours, which connects to the Virgo cluster through the Virgo filament. Beyond Virgo, the Hydra-Centaurus filament leads directly into the Great Attractor basin. From there, a continuous flow extends even farther outward toward the Shapley concentration, 650 million light-years away. It is as if our galaxy lies within a vast cosmic river system. Local group Virgo, Hydra Centaurus, Great Attractor, Shapley supercluster. Each step represents a deeper gravitational valley in the landscape of the cosmic web, the architecture of Laniakea. Mapping the cosmic web requires measuring not only where galaxies are, but where they move. The Cosmic Flows project, led by Tully and Courtois, uses thousands of galaxy distance measurements to reconstruct their velocities and infer the underlying gravitational field. The resulting visualization of Laniakea is breathtaking, a fluid-like structure in which galaxies flow like streams converging toward a single gravitational basin. In that map, the Great Attractor sits at the bottom of the basin, the gravitational sink of Laniakea, while beyond its ridge, galaxies flow toward the Shapley supercluster, another deeper basin farther away. Each of these basins defines a supercluster domain. Boundaries between them are not physical walls, but caustic surfaces where flow lines diverge, analogous to continental divides on Earth. The Great Attractor lies exactly at the ridge between these domains, shaping the motion of galaxies on both sides. This framework revealed a crucial insight. What we once thought were isolated superclusters are actually parts of a continuum of gravitational basins spanning the entire local universe, filaments of fire and ice. If you could see the Great Attractor and its surroundings with X-ray vision, the view would be spectacular. Filaments of hot plasma stretch between clusters, glowing at tens of millions of degrees Kelvin. These filaments contain the warm, hot intergalactic medium, gas, that bridges the space between galaxies, accounting for much of the universe's missing baryons. O quote. Within Hydra Centaurus, X-ray observatories have detected WIM filaments tens of millions of light-years long, connecting clusters like Norma, Parvo, and Centaurus. These filaments are both gravitational and thermal highways. Matter flows along them, while shock waves heat the gas to extreme temperatures. Each filament acts like a conveyor belt, slowly feeding galaxies into the Great Attractor's gravitational basin over billions of years. In this way, the cosmic web is not static, but alive, continuously funneling material into deeper wells. The universe as a fluid. Modern cosmologists often describe the cosmic web using the language of fluid dynamics. On large scales, galaxies behave like particles suspended in a fluid flow, tracing the gradients of gravitational potential. In this analogy, the Great Attractor is a vortex, a convergence zone where gravitational currents meet. The Shapley concentration is a deeper vortex downstream, and the local void is the high-pressure bubble pushing us toward it. This hydrodynamic view transforms the universe from a static map into a dynamic flow field. It's not just that galaxies sit in place and gravity pulls them, rather, the entire fabric of matter moves, bends, and streams like a slow-motion ocean of galaxies. Our motion in the cosmic current. Through these interconnected flows, the Milky Way drifts through space at 600 kilometers per second, carried along by a current that began forming billions of years ago. Our motion, measured relative to the CMB, aligns precisely with the direction of the Great Attractor's basin, a trajectory shared by countless other galaxies in Laniakea. To imagine this is to picture a leaf floating on a river whose scale defies imagination. Each wave is a cluster, each eddy a supercluster, and the river itself extends across hundreds of millions of light years. It's a humbling thought. Everything we see in the night sky, every familiar star and nebula, moves together within this cosmic current, guided by gravity's invisible architecture. The deep implications. The Great Attractor's role in the cosmic web reminds us that structure and motion are inseparable in the universe. The web is not a static scaffolding frozen in time. It is a dynamic, evolving system. Gravity builds the web, dark energy stretches it, and the cosmic expansion continuously reshapes it. In this dance of matter and void, the Great Attractor serves as a bridge between the local and the cosmic, between the structures we can map and the larger flows that extend far beyond. It also anchors one of the most profound realizations in modern cosmology, that we are not passive observers, but participants in a vast gravitational system. Every motion of our galaxy, every drift of our local group, every ripple in the CMB reflects the shape of this cosmic web, a universe connected by gravity. When you look toward the southern sky, past the bright spine of the Milky Way, you are not just looking at stars. You are gazing along one of the filaments of the cosmic web, a gravitational highway that links our galaxy to a structure hundreds of millions of light years away. Along that invisible path lie clusters, superclusters, and rivers of dark matter. Through them, the Great Attractor exerts its quiet influence, shaping the flow of galaxies across Laniakea and beyond. It is part of the architecture of everything, a junction in a network that spans the cosmos. And somewhere, far along that same filament, lies an even greater gravitational domain waiting to be understood. Beyond the Great Attractor, for decades, the Great Attractor was treated as the end point of our galactic journey, the gravitational destination of everything in our cosmic neighborhood. But as astronomers learned to see deeper into space, a new picture began to emerge. The Great Attractor was not the end. It was only the beginning of a far larger flow, a gravitational descent into the deeper valleys of the universe. Beyond the Great Attractor lies another structure, vaster and heavier than anything near it. The Shapley concentration, an enormous supercluster complex, roughly 650 million light-years away in the direction of Centaurus and Hydra, containing thousands of galaxy clusters and hundreds of trillions of solar masses. It is, in many ways, the true behemoth toward which our entire region of the cosmos ultimately drifts. From the Great Attractor to Shapley, in the 1980s, when the Great Attractor was first identified, astronomers assumed its gravitational influence was sufficient to explain all observed peculiar velocities, the motion of galaxies deviating from the Hubble expansion. But by the early 1990s, redshift surveys were reaching farther into the southern sky, and they uncovered something surprising. Even galaxies beyond the Great Attractor region were streaming in the same general direction. If the Great Attractor alone were responsible, the flow should have slowed beyond its center. Instead, it continued as if a second, even larger mass lay farther away, continuing the pull. The suspicion grew with data from surveys such as the Southern Sky Redshift Survey, SSRS-2, and the IRAS Point Source Catalog, PSCs. Both revealed an immense overdensity centered around galactic longitude to 312 degrees, latitude plus 30 degrees at a distance of roughly 200 megaparsecs, 650 million light-years. This was the Shapley concentration, named after the American astronomer Harlow Shapley, who had catalogued rich clusters in that region as early as the 1930s. Only now did astronomers realize just how massive and extensive it was, the largest mass in our cosmic neighborhood. The Shapley concentration is a supercluster of superclusters, centered on the Shapley supercluster, SCL 124. It contains over 25 rich Abell clusters within a volume roughly 100 million light-years across, and has an estimated total mass exceeding 10 to the power of 17 solar masses, 10 times greater than the Great Attractors. At its core lies the Abell 3558 cluster, part of the A 3558 complex, surrounded by other massive clusters such as Abell 3562, Abell 3556, Abell 3500, and Abell 3574. Each of these contains thousands of galaxies and emits intense X-rays from million-degree intracluster gas. X-ray data from ROSAT, XMM Newton, and Chandra reveal temperatures between 5 times 10 to the power of 7 and 8 times 10 to the power of 7 Kelvin, indicating tremendous gravitational potential. These clusters are embedded in a dense filamentary network extending over 150 million light-years, forming one of the largest contiguous overdensities known in the local universe. If the Great Attractor is a mountain range of gravity, the Shapley concentration is the continent that dwarfs it, our galaxy's true trajectory. When cosmologists map galactic motion using the cosmic flows datasets, including the work of R. Brent Tully, Hélène Courtois, and Yehuda Hoffman, a clear picture emerges. Our local group, along with the Virgo and Hydra Centaurus clusters, is streaming along a gravitational gradient that leads beyond the Great Attractor toward Shapley. In velocity space reconstructions, the flow lines resemble a river that passes through the Great Attractor before descending toward a deeper gravitational basin downstream. This means that while the Great Attractor dominates our local motion, it is itself being pulled by the immense gravity of Shapley. The analogy of cosmic hydrology is apt. If Laniakea is a watershed, then the Great Attractor is the main valley within it, and Shapley is the ocean beyond the ultimate gravitational sink in our region of the universe. Evidence from bulk flows. One of the most striking confirmations of Shapley's influence comes from measurements of bulk flow, the average peculiar velocity of galaxies across large volumes of space. In 2010, surveys such as the 6DF Galaxy Survey, 6DFGS, and Cosmic Flows 2 revealed that galaxies across a region 600 million light-years wide were moving coherently toward the Shapley direction, with velocities up to 400-500 kilometers per second. This bulk flow extends far beyond the scale of the Great Attractor itself. Later, Cosmic Flows 3 refined the data, showing that while the Great Attractor accounts for a large fraction of our velocity, it cannot explain the magnitude of motion observed at larger distances. The excess motion aligns almost perfectly with the direction of Shapley's gravitational center. In short, we are not just falling into the Great Attractor, we are sliding along a gravitational slope that leads deeper into Shapley's colossal domain. The Shapley concentration in context. To grasp the enormity of Shapley, consider this. The Virgo cluster contains roughly 1,300 galaxies and a mass of 10 to the power of 14 solar masses. The Norma cluster, anchor of the Great Attractor, is about 10 to the power of 15 solar masses. But Shapley's main cluster complex alone contains tens of thousands of galaxies and a total mass exceeding 10 to the power of 17 solar masses, equivalent to 100,000 Milky Ways. The entire structure stretches across more than 650 million light-years, encompassing clusters such as Abell 3000, 558, a 3,562, and a 3,571, connected by dense filaments of dark matter and hot gas. These clusters are bound together not just by visible galaxies, but by vast dark matter halos, forming one of the deepest gravitational wells in the known universe, the multi-attractor universe. The realization that Shapley dominates the large-scale flow beyond the Great Attractor led to a new framework in cosmology, the multi-attractor model. Rather than a single gravitational center pulling everything, the local universe is governed by several major attractors, each corresponding to massive superclusters. The Virgo attractor, influencing local motions within 50 million light-years. The Great Attractor, Hydra Centaurus, affecting galaxies within about 250 million light-years. The Shapley concentration, influencing flows out to nearly 650 million light-years. Superimposed on these are repulsive regions, large cosmic voids where matter density is low. The dipole-repeller hypothesis, proposed in 2017 by Hoffman, Courtois, and Tully, explains our motion as a combination of gravitational attraction toward Shapley and repulsion from the local void, an immense underdense region adjacent to our local group. Together, these forces create a gravitational dipole. We are pulled and pushed simultaneously, our path through space defined by the balance of mass and emptiness. The dipole repeller pushed by the void. The concept of a repeller may sound counterintuitive. Gravity only attracts, it doesn't push. But in a universe filled with uneven density, regions with less matter effectively act as repellers. Imagine space-time as a stretched rubber sheet. Dense regions create valleys, while voids are like raised hills. Matter naturally flows from the hills into the valleys. The local void, a cavity about 150 million light-years across, adjacent to our local group, acts as such a hill pushing galaxies toward the Great Attractor and Shapley. In 2017, velocity field reconstructions using cosmic flows, 3 data visualized this directly. Flow lines diverged from the local void and converged toward the Great Attractor and then Shapley. The result was a cosmic dipole, one side dominated by attraction, the other by repulsion. This discovery elegantly explained why our 600 km per second velocity relative to the CMB has both magnitude and direction consistent with being pushed out of a void while pulled into the Shapley basin. A dynamic cosmic balance. The interplay between attractors and voids defines the kinematic landscape of our region of the universe. The Great Attractor is not a fixed point but a dynamic node, a gravitational relay passing the flow onward. Shapley, farther away, represents the deeper terminal basin in this flow. Numerical simulations of large-scale structure formation show that superclusters like Hydra, Centaurus, and Shapley form along the same filament of the cosmic web. Over cosmic time, smaller overdensities merge into larger ones, deepening the gravitational potential. This means the Great Attractor and Shapley are linked parts of the same filament, a continuous bridge of matter, gas, and dark matter stretching over 500 million light-years. Our galaxy, in turn, is moving along that bridge, a small particle caught in a slow, majestic current. Seeing the flow, visualizations produced by the Laniakea and Shapley flow models are stunning. Galaxies are shown as coloured dots drifting through a 3-dimensional volume, their trajectories bending gently toward gravitational centres. In these models, the Milky Way lies near the boundary of 2 flow domains, one dominated by the Great Attractor and another extending toward Shapley. The flow vectors curve gracefully, like rivers merging at a delta before plunging toward the deeper ocean beyond. Every motion, from the rotation of the local group to the drift of entire clusters, is part of this immense pattern. When we measure the CMB dipole, we are capturing the echo of that flow, the collective motion of tens of thousands of galaxies responding to the universe's largest gravitational wells. Shapley and the limits of observation, at a distance of 650 million light-years, Shapley lies near the observational limit, where peculiar velocities become difficult to distinguish from cosmic expansion. Yet, even at that distance, its influence is measurable. Galaxy counts from the 2 Mass Redshift Survey and the 6DF Galaxy Survey show a clear overdensity in Shapley's direction. X-ray data confirm that the gas between its clusters is heated to tens of millions of Kelvin, consistent with continuous accretion and merger activity. Despite its distance, Shapley's gravitational potential may account for as much as 1/3 of our galaxy's total peculiar velocity relative to the CMB, a remarkable testament to its power. In simulations of the local universe, the Great Attractor appears as a middle step in a gravitational hierarchy that extends outward for hundreds of millions of light-years. Our Milky Way is thus both falling into the Great Attractor and being drawn onward toward the Shapley concentration beyond it. The scale of influence. From Earth, the line connecting the local group, the Great Attractor, and Shapley stretches across nearly 700 million light-years, one of the longest coherent gravitational alignments known. Within this alignment, the local group resides about 60 million light-years from the Virgo cluster. The Virgo cluster lies roughly 150 million light-years from the Great Attractor. The Great Attractor is about 400 million light-years from Shapley. Each step is a rung in a cosmic ladder of attraction. The cumulative effect is our total motion through the universe, a dance choreographed by structures we can barely comprehend. The long future. In the far future, the expansion of the universe accelerated by dark energy will eventually stretch the cosmic web so that distant structures like Shapley recede beyond our observable horizon. But gravitationally bound regions like the Great Attractor and Centaurus will remain intact. Over tens of billions of years, galaxies within Laniakea will continue to merge, forming a single supergalaxy at the core of the Great Attractor region. Beyond that, the rest of the universe will fade from view. We will never reach Shapley. The expansion of space ensures that its distance grows faster than we can fall toward it. Yet, for now, we can still measure its pull, feel its gravity written in the motion of our galaxy. The view from here, when you look into the southern sky toward Centaurus, you are looking along a gravitational highway, a line of descent stretching from the Milky Way through the Great Attractor all the way to the Shapley concentration 650 million light-years away. That invisible line defines our place in the cosmic web. It is both a trajectory and a lineage, the direction of fall for countless galaxies linked by the unseen hand of gravity. What began as a mystery about why our galaxy moves has become a revelation about the structure of the universe itself, that we are part of a flow extending across intergalactic space, carried by gravity from one colossal basin to the next. The Great Attractor, once the ultimate destination, is now recognized as a passage, a bridge between local and cosmic scales, leading into an even grander structure beyond, and beyond that, perhaps, still greater attractors await deeper valleys in the ever-expanding landscape of the universe, hidden beyond the reach of light, but still written in the motions of the galaxies around us. Mysteries and future observations. The Great Attractor, once a blank spot in our maps, has become a cornerstone of modern cosmology. Yet even now, almost half a century after its discovery, it remains partly hidden, its full structure, extent, and nature still uncertain. For all we've revealed through infrared, radio, and X-ray vision, the Great Attractor continues to resist complete understanding. It is both a triumph of observation and a reminder of our limitations. Each discovery opens new questions. How deep is its gravitational basin? How is its mass distributed between dark and visible matter? How does it connect to the larger flow toward Shapley? And, perhaps most tantalizingly, how many other attractors lie beyond, too distant or obscured for us to yet perceive? The problem of the zone of avoidance. Even with the power of modern telescopes, the zone of avoidance remains one of astronomy's greatest observational barriers. The Milky Way's thick midplane of stars, dust, and molecular clouds still obscures about 20% of the extragalactic sky. While infrared and radio waves can pierce much of that, not all wavelengths escape unscathed, especially those needed to measure faint, distant galaxies with high redshift precision. This means that our maps of the Great Attractor and the Centaurus region are still patchy. Filaments may crisscross the zone unseen. Entire clusters could lurk just beyond detection. Even today, the census of galaxies in the region remains incomplete, and small uncertainties in distance measurements can ripple through gravitational models, altering our understanding of how mass is distributed. Astronomers call it the hidden universe, a vast stretch of sky we are only now beginning to uncover. Measuring peculiar velocities, the ongoing challenge. Peculiar velocity, the difference between a galaxy's observed redshift and what we'd expect purely from cosmic expansion, is one of the most powerful tools for mapping gravitational flows, yet it is also one of the hardest quantities to measure accurately. To determine a galaxy's peculiar velocity, we must first know its true distance. That distance is derived using empirical relationships, like the Tully-Fisher relation for spirals and the fundamental plane for ellipticals, both of which link intrinsic brightness or surface brightness to physical properties like rotation, speed, or stellar dispersion. But each relation comes with scatter and calibration uncertainty. For distant galaxies tens or hundreds of millions of light-years away, small percentage errors in distance translate to hundreds of kilometers per second of velocity uncertainty. The result? Noisy maps of motion that require statistical smoothing over thousands of galaxies. Projects like Cosmic Flows 3 have improved precision dramatically, but further progress will demand even more extensive surveys with higher resolution and uniform calibration, the next generation of sky surveys. The coming decade promises to revolutionize our understanding of the Great Attractor and the universe's large-scale flows. Several next-generation missions, some already launched, others soon to follow, are designed specifically to probe the structure of hidden regions and map the cosmic web in unprecedented detail. 1. Euclid, ESA, launched 2023. The Euclid Space Telescope, a mission by the European Space Agency, is designed to map the geometry of the dark universe. Equipped with a 1.2-meter mirror and 2 instruments, a visible imager VIS, and a near-infrared spectrometer, Euclid will observe over 1/3 of the entire sky. Cataloguing billions of galaxies out to redshift Z is approximately equal to 2. Its ability to measure both shapes and redshifts will allow astronomers to trace dark matter distribution through weak gravitational lensing. For regions like the Great Attractor, Euclid's near-infrared sensitivity will penetrate deeper through dust, refining mass models and detecting new filaments hidden behind the Milky Way's plane. 2. JWST, NASA, ESA, CSA, launched 2021. The James Webb Space Telescope operates primarily in the infrared, giving it the power to see through galactic dust and observe faint, distant galaxies. Although JWST's field of view is small compared to survey missions, its extreme sensitivity makes it ideal for studying individual galaxies and clusters within obscured regions. By examining infrared spectra, astronomers can measure stellar populations, metallicities, and star formation rates of galaxies within the Great Attractor zone, shedding light on how dense environments affect galactic evolution. 3. SKA, Square Kilometre Array, under construction. Perhaps the most transformative project for mapping hidden structures is the Square Kilometre Array, SKA, a radio telescope network being built across South Africa and Australia. When completed in the 2030, SKA will have the sensitivity to detect faint 21 cm hydrogen emissions from galaxies out to redshift Z is approximately equal to 1.5, covering billions of light-years. Its ability to penetrate the zone of avoidance will finally provide a near-complete map of the southern sky, revealing galaxies that have remained invisible to optical astronomy. SKA's velocity data will enable precision mapping of the Great Attractor's flow field and clarify how its influence transitions into Shapley's domain. 4. Vera C. Rubin Observatory, formerly LSST. While not optimized for the obscured zone of avoidance, the Rubin Observatory in Chile will produce deep, wide-field imaging of the visible sky, measuring motions of galaxies outside the obscured regions and improving constraints on large-scale flow models. Its time-domain observations will also allow for transient studies of cluster environments within the Great Attractor region, capturing supernovae and active galactic nuclei that trace the distribution of mass in real time, mapping the invisible dark matter and dark energy. Although the Great Attractor's pull is obvious, what causes it physically remains partly hidden in darkness. Visible galaxies and hot gas account for only about 15% of its gravitational mass. The rest must be dark matter, a substance we have never observed directly. Future missions, like Euclid and the Nancy Grace Roman Space Telescope, will measure subtle distortions in background galaxies due to gravitational lensing. These distortions allow astronomers to map the underlying dark matter distribution without relying on visible light. Such lensing maps could reveal the full three-dimensional extent of the Great Attractor's dark matter halo and its connection to the filaments leading toward Shapley. At the same time, these missions will probe the role of dark energy, the mysterious force driving cosmic acceleration. While dark energy acts on the largest scales, understanding its interaction with structures like the Great Attractor will help refine models of how the universe evolves between gravity's pull and expansion's push. Unanswered questions. Even with all this progress, the Great Attractor remains surrounded by mysteries. Among the key open questions are, what is its true boundary? Is the Great Attractor a discrete structure or merely the densest part of the larger Laniakea Basin? The boundary between gravitational domains remains fuzzy and depends on how flow lines are defined. How does its mass evolve over time? Mergers between clusters continue to reshape the region. X-ray and radio evidence suggests that the Norma cluster is still accreting matter. How fast is it growing? Will it merge with Centaurus or Hydra in the distant future? What is the detailed composition of its dark matter halo? Are dark matter distributions smooth or clumpy and filamentary? The answer has implications for particle physics and the formation of cosmic structure. What lies beyond Shapley? Is Shapley the final gravitational basin in our region, or part of an even greater alignment of mass concentrations? Some redshift surveys hint at overdensities farther still. Near Z is approximately equal to 0.05, 0.07, that may continue the cosmic filament beyond Shapley's edge. How do voids shape cosmic motion? The dipole-repeller hypothesis remains a powerful explanation, but the detailed geometry of nearby voids is still poorly known. New surveys will help map their extent and confirm whether our galaxy's motion truly results from a combined push and pull, the frontier of visualization. Understanding structures like the Great Attractor requires not just data, but vision, turning streams of numbers into maps of motion that the human mind can grasp. Projects like Cosmic Flows 4, Thule's Laniakea visualizations, and Pomered's 3D reconstructions have revolutionized how we visualize the local universe. Using supercomputing and color-coded velocity fields, these models show galaxies flowing like luminous particles through the dark, curving toward invisible basins. Future visualization work will merge observational data with machine learning-based reconstructions, allowing researchers to infer missing information in obscured zones. The result will be a continuously updating, near-complete digital model of the local cosmos, one that evolves as new observations arrive from Euclid, SKA, and JWST. A new cartography of the cosmos. Just as ancient explorers charted the oceans without knowing what lay beyond the horizon, cosmologists today are mapping the hidden universe beyond our galactic plane. Each new instrument is another compass. Each new survey adds a coastline to our cosmic atlas. The Great Attractor, once invisible, now stands as a beacon for what can be achieved when ingenuity meets persistence. Its discovery led to the concept of superclusters, to the definition of Laniakea, and to the recognition that our galaxy is not adrift but bound to a vast cosmic river of motion. In the coming decades, the next generation of telescopes will refine that map, perhaps revealing that the Great Attractor itself is only a ripple in a still larger current, extending beyond the limits of what we can yet imagine. The endless horizon. Every time we peer deeper into the cosmos, the universe grows larger and more intricate. The Great Attractor and Shapley concentration remind us that cosmic discovery is never finished. It is a continuous process of unveiling. We have measured their gravitational influence, mapped their galaxies, and glimpsed their hot plasma halos. But the space between those hidden filaments, faint galaxies, and dark matter streams remains largely uncharted. Perhaps in a century, future astronomers will look back on this era as we look back on the first star charts, bold, incomplete, and utterly transformative. For now, we stand at the threshold our telescopes pointed into the obscured heart of the Milky Way, searching for the forces that pull us through the universe. Every photon we collect, every redshift we measure, brings us closer to understanding the invisible architecture that defines our cosmic home, the gravitational symphony. From the moment the first particles cooled out of the primordial fireball, the universe has been orchestrated by a single force, gravity. It is the quiet composer behind the structure of everything, the invisible hand that writes the score of motion and form. You feel its pull every second of your life, yet the same force that keeps your feet on the ground is also what binds galaxies into clusters, clusters into superclusters, and superclusters into the cosmic web itself. Gravity is the link between the fall of an apple and the drift of the Milky Way toward the Great Attractor, 600 kilometers every second. Across every scale, from the familiar to the unfathomable, the story is the same. Matter curves space-time, and space-time tells matter how to move. The universal architect. Gravity is paradoxical, at once the weakest and most powerful of the fundamental forces. Between two protons, its strength is 10 to the power of 38 times weaker than electromagnetism. Yet across astronomical distances, it dominates everything. Unlike the other forces, gravity never cancels out, it only adds. Every particle of matter in the universe contributes to the total gravitational field, no matter how faintly. Einstein's general theory of relativity, published in 1915, gave us the mathematical language to describe this, not as a force transmitted through space, but as the curvature of space-time itself. Massive objects bend the geometry around them, and smaller ones follow the natural curves, geodesics, within that geometry. On small scales, this curvature makes planets orbit stars, and stars orbit galactic centers. On large scales, it sculpts the distribution of matter into filaments, walls, and clusters, the same patterns we now trace through Laniakea and the Great Attractor. Gravity builds hierarchies. Every structure is nested within a larger one. Stars orbit within galaxies. Galaxies orbit within groups and clusters. Clusters drift through superclusters. And all of them follow the contours of the cosmic web, descending into gravitational valleys like notes resolving toward a chord. The universe is a symphony of falling, from local orbits to cosmic currents. To understand the scale of this harmony, start small. The Earth orbits the Sun at 30 kilometers per second, a balance of kinetic energy and gravitational attraction. The Sun orbits the center of the Milky Way at 220 kilometers per second, completing one galactic year every 230 million years. But the Milky Way itself is not stationary. Together with the Andromeda Galaxy, it is part of the Local Group, both spiraling toward a future collision roughly 4 billion years from now. That mutual attraction is local music, a duet in a gravitational chamber. Zoom out further, and the local group orbits within the local sheet, which drifts toward the Virgo cluster, 60 million light-years away. Virgo, in turn, flows into the Hydra Centaurus supercluster, whose mass defines the Great Attractor. And beyond that, everything flows toward Shapley, the deepest tone in this vast orchestra of matter. Each layer plays its own tempo, fast on the small scale, slow on the grand. The melody of galaxies moves not in seconds, but in millions of years, and yet it follows the same physical rhythm that makes an apple fall. Resonances in the cosmic web. When cosmologists run large-scale simulations, such as the Millennium Simulation or Illustris TNG, what emerges looks almost alive. Clusters pulse, filaments quiver, and density waves ripple through the dark matter scaffold like sound through air. These are not literal vibrations, but the gravitational equivalent density resonances propagating through the cosmic medium. As filaments grow, matter flows toward their densest points, overshooting equilibrium, then sloshing back. Over billions of years, these oscillations create patterns that repeat across scales, a gravitational resonance that gives the universe its structure. In 2001, the Sloan Digital Sky Survey revealed an imprint of one such ancient resonance, the Baryon Acoustic Oscillation, BAO. These are frozen sound waves from the early universe, ripples left over from when radiation and matter were tightly coupled. Their wavelength, about 500 million light-years, still defines the spacing of galaxy clusters today. Even across 13.8 billion years, the cosmos carries the memory of its own first harmonics. Dark matter, the silent bass line. If gravity is the symphony, dark matter is its bass section, inaudible, but essential. Though invisible, dark matter sets the rhythm of structure formation. Its gravitational wells provide the scaffolding into which gas and stars fall, amplifying density contrasts and giving form to the web. Without dark matter, galaxies would never have condensed. The universe would remain a thin, diffuse fog. Yet dark matter itself emits no light. We detect it only through its gravitational effects, how it bends, starlight gravitational lensing, and speeds up the motion of galaxies inside clusters. Observations from the Planck mission indicate that dark matter accounts for 26.8% of the universe's energy density, while normal matter makes up just 4.9%. The rest is dark energy, an even more mysterious element driving cosmic expansion. The Great Attractor's extraordinary pull cannot be explained by luminous matter alone. Its mass-to-light ratio suggests that 5 to 6 times more dark matter than baryonic matter must be concentrated within its gravitational basin. It's the invisible baseline that gives the structure its depth and power. Galactic choreography. Galaxies don't move randomly. They interact like dancers in a complex choreography, their orbits influenced by surrounding gravitational fields. When two galaxies approach, their mutual attraction distorts them, flinging out long tidal tails of stars and gas. If they merge, their dark matter halos blend, deepening the gravitational note they play in the cosmic symphony. The Milky Way and Andromeda are already beginning this dance. In about 4.3 billion years, they'll collide, merging into a single elliptical galaxy, sometimes nicknamed Milkdromeda. Even as this local merger unfolds, the entire system will continue drifting toward the Great Attractor, a waltz nested within a galactic tide. Every such interaction feeds upward into larger patterns. Clusters merge into superclusters, superclusters into filaments, and filaments stream toward nodes like Hydra Centaurus and Shapley. The scale changes, but the choreography remains the same. Gravity drawing masses together, until equilibrium or collision resolves the tension. Gravity's counterpoint, expansion. Every symphony needs contrast. Against gravity's unifying melody stands the counterpoint of cosmic expansion. Since Edwin Hubble's discovery in 1929, we've known that galaxies, on average, are receding from each other. Space itself stretches, increasing the distance between clusters. Yet on smaller scales, gravity overcomes expansion, binding matter into stable configurations. The Great Attractor represents one of those victories, a region where local gravity cancels out the cosmic expansion, creating a gravitational eddy in the universe's flow. Galaxies caught inside it no longer recede passively. They fall inward, deviating from the Hubble flow. Einstein's equations predict this tension perfectly. Expansion dominates on large scales, but curvature wins in regions of high density. The universe is thus a constant duet between the two forces, one pulling inward, the other pushing outward. The resulting rhythm is what defines the structure of the cosmos itself, the mathematics of harmony. At the core of all this motion lies a simple relation. Acceleration equals phi, where phi is the gravitational potential, a measure of how deep the local valley in space-time is. In practical terms, galaxies move downhill toward regions of lower potential, just as rivers flow toward lower terrain. The Great Attractor is a depression in this gravitational landscape, the Shapley concentration, an even deeper one beyond it. When cosmologists map peculiar velocities, they are, in effect, tracing the contours of this potential, like mapping the shape of a song by watching how air moves when it's played. Each cluster, each filament, is a note in the gravitational composition of space-time, a symphony across time. What makes gravity's music extraordinary is its slowness. The crescendos of galactic mergers unfold over billions of years. The decays of voids last longer than the age of life on Earth. Yet on cosmic scales, time is only another instrument. The universe's first chords sounded in the primordial plasma, when fluctuations in density set up pressure waves in the early cosmic fluid. The last notes will fade trillions of years from now, when the final black holes evaporate and gravitational interactions become too weak to stir new structure. Between those extremes lies the movement we inhabit, a slow, magnificent passage in which galaxies drift, merge, and flow through an ever-changing web of attraction, the human scale of gravity. We often imagine ourselves distant from such grandeur, but the same physics operates everywhere. The tides that lift and lower Earth's oceans are small echoes of the same force that drives the Milky Way toward the Great Attractor. The curvature of space-time around Earth is gentle, around a galaxy immense, around the Great Attractor profound. Yet the principle never changes. Where there is mass, there is curvature. Where there is curvature, there is motion. To understand gravity is to recognize unity, the same fundamental law shaping pebbles and planets, atoms and clusters. Every human gesture is accompanied by the faint whisper of the same gravitational field that guides entire galaxies across millions of light years. The Great Attractor as a conductor. Within this symphony, the Great Attractor acts as a local conductor, coordinating the motion of nearby galaxies in its region of space-time. Its gravitational pull organizes hundreds of thousands of galaxies into coherent flow, aligning velocities like musicians, following a shared rhythm. Yet even this conductor follows a higher authority, the deeper gravitational key set by the Shapley concentration. In this nested hierarchy, each structure both leads and follows, contributing to a composition without beginning or end. If you could compress the timescale of the universe into a single hour, the cosmic web would shimmer and pulse like a living organism, filaments flexing, clusters merging, voids expanding. Gravity would be the silent music holding it together toward the next movement. Every discovery, every survey and simulation adds new instruments to this orchestra. Infrared telescopes reveal hidden harmonies. Radio observatories trace the deep bass lines of neutral hydrogen. X-ray detectors capture the percussion of colliding clusters. Soon, gravitational wave observatories like LISA will add a new dimension, letting us literally hear the vibrations of merging black holes within these cosmic structures. In this coming era, astronomy will no longer be just the study of light, but of motion itself, the study of how space-time hums under the weight of matter. And at the center of it all remains the same note, the gravitational pull that draws our galaxy silently, inexorably toward the Great Attractor, the infinite score. The universe, at every moment, performs a composition that began 13.8 billion years ago and will continue long after the last star fades. The Great Attractor, the Shapley concentration, and every cluster between them are movements within that infinite score written not in sound, but in the motion of galaxies through curved space-time. Gravity does not simply pull, it conducts, it arranges, it gives meaning to motion, turning chaos into form. And though we may never hear the music directly, every orbit, every fall, every galactic drift is a note within the same eternal symphony. Echoes of the invisible. For centuries, astronomy meant one thing: light. From Galileo's telescope to the Hubble Space Telescope, every image, every discovery was born from photons, particles of light travelling across the void. But light has its limits. It can be blocked, absorbed, redshifted, or scattered. The Great Attractor itself hides in a place where light struggles to reach us behind the Milky Way's dense disk, inside the zone of avoidance. To see beyond light, we've had to learn to listen. In the last 2 decades, a new astronomy has begun to emerge, one that hears the universe through gravitational waves, neutrinos, radio pulses, and cosmic background radiation. These are not beams of light, but echoes of the invisible, carrying information about regions and events that optical telescopes will never reach. It is through these signals that we are beginning to sense what lies deeper within the Great Attractor and what the fabric of the universe sounds like beneath the surface of sight. The universe beyond light. In the 19th century, light was thought to be the ultimate messenger. But in 1916, Einstein predicted another kind of radiation, gravitational waves ripples in space-time produced when massive objects accelerate. For a century, they remained a mathematical curiosity. Then, in September 2015, detectors at LIGO in Louisiana and Washington State recorded a faint, rhythmic signal. The merger of 2 black holes, 1.3 billion light-years away. That detection was not just a triumph of engineering, it was a transformation of perception. For the first time, humanity had heard gravity move. Since then, over 90 gravitational wave events have been catalogued by the LIGO-Virgo-Cagra network, including black hole and neutron star collisions. Each detection adds to a growing symphony of space-time vibrations, and each teaches us how matter behaves in conditions too extreme for light to escape. But gravitational waves can do more than confirm relativity. They can also illuminate the hidden universe regions, like the Great Attractor, where light is obscured but massive mergers still occur. Future observatories like the Laser Interferometer Space Antenna, ELISA, scheduled for launch in the 2030, will listen to lower frequency waves from supermassive black hole binaries, the kind that dwell in galaxy clusters and superclusters. If such titans merge within the Great Attractor's core, their gravitational symphony will echo across hundreds of millions of light-years, revealing activity deep inside the hidden structure, the whisper of the cosmic backgrounds. Long before stars, galaxies, or clusters existed, the universe itself rang with sound. In its first 380,000 years, the primordial plasma of particles and light oscillated like a drum, its density waves imprinting patterns on the cosmic microwave background. CMB, the faint afterglow of the Big Bang. We can still detect those ripples today. The Planck satellite, launched by the European Space Agency in 2009, measured temperature differences of just millionths of a degree, revealing a map of these ancient vibrations. Those patterns tell us not only how matter was distributed in the early universe, but how it later condensed into the filaments and attractors we see now. The Great Attractor's location and gravitational pull are both consistent with the CMB's dipole anisotropy, the fact that the cosmic background appears slightly hotter in one direction and cooler in the opposite. That temperature difference corresponds exactly to our galaxy's motion through space. 600 kilometers per second toward the Centaurus Norma region. In other words, the oldest light in the universe records our fall into the Great Attractor like a cosmic weather vane. Even after 13.8 billion years, the background radiation still remembers the direction of our journey. But there is an even older Echo 1 that predates light itself, the cosmic neutrino background. Roughly 1 second after the Big Bang, when the universe was still an ocean of particles, a ghostly species decoupled from matter and began streaming freely through space, neutrinos. These nearly massless particles rarely interact with anything. Trillions pass through your body every second without leaving a trace. Yet collectively, they fill the universe, carrying information from its earliest moments. This cosmic neutrino background, Canubi, is the oldest fossil we can imagine, a record of conditions long before photons could move freely. Though we haven't detected the CNUB directly yet, its effects are measurable. Data from Planck, combined with baryon acoustic oscillations, confirm that these primordial neutrinos influence the formation of structure, slightly damping the growth of small-scale density fluctuations. Without them, regions like the Great Attractor might have collapsed faster. With them, the cosmic web grew more gently, more rhythmically. Future detectors, such as Ptolemy, an ambitious neutrino experiment in Italy, aim to capture these relic neutrinos directly, giving us a true sound recording of the universe's first second. When that happens, we'll hold a piece of the invisible prelude to all cosmic structure, the X-ray and radio eyes of the hidden universe. If light fails, we turn to other messengers that can pierce the cosmic fog. In the Great Attractor's region, optical telescopes are nearly blind, but X-rays and radio waves cut through dust with ease. The Rosat, Chandra, and XMM Newton observatories have revealed hot intracluster gas glowing at tens of millions of degrees, tracing the dense skeleton of galaxy clusters like Norma and Centaurus. Meanwhile, radio astronomy has opened a new frontier. Neutral hydrogen emits radiation at a wavelength of 21 centimeters, which can travel unimpeded through the Milky Way's obscuring dust. Instruments like the H.I. Parkes All-Sky Survey and the ongoing Wallaby Survey with the Australian SKA Pathfinder, ASCAP, have used this emission to chart galaxies hidden behind the galactic plane. These surveys have already uncovered new structures, filaments and clusters that fill in gaps in the Hydra Centaurus region, providing a clearer picture of the Great Attractor's boundaries. As the Square Kilometre Array, SKA, comes online in the next decade, it will map millions of new galaxies, turning the once blank zone of avoidance into a complete three-dimensional atlas. listening to the universe's deepest tones. Gravitational waves, neutrinos, and cosmic background radiation all tell different parts of the same story. Together, they transform the universe from a silent void into a living, resonant medium. If light is treble, these are the bass and percussion carrying the deeper frequencies of cosmic history. Gravitational waves reveal the motion of mass, the heartbeat of space-time. Neutrinos carry the faint echo of the universe's infancy, a whisper of its first breath. X-rays and radio waves unveil the energy and structure hidden by dust and darkness. Each messenger complements the others, painting a multi-dimensional portrait of structures like the Great Attractor, not as static shapes, but as dynamic, evolving entities. The rise of multi-messenger cosmology. In the past decade, a new scientific paradigm has taken hold. Multi-messenger astronomy, the study of the universe using all possible signals, not just electromagnetic radiation. In 2017, LIGO and Virgo detected gravitational waves from the merger of two neutron stars. Within seconds, observatories across the world turned to the same patch of sky and captured the corresponding gamma-ray burst and optical afterglow. It was the first event ever observed through both gravitational and electromagnetic channels. This synergy changed everything. For the first time, scientists could watch the same cosmic event unfold in multiple languages. The combination of signals revealed not only the energy of the explosion, but also the elements created gold, platinum, and uranium forged in the collision's fiery heart. Applied to regions like the Great Attractor, this approach could reveal the unseen dynamics of its massive clusters. When black holes merge or galaxies collide in its core, gravitational waves may ripple outward long before light can escape the surrounding dust. With multi-messenger networks, we may one day pinpoint those hidden cataclysms directly, confirming that the Great Attractor is not just a static overdensity, but a living, evolving structure. The unseen universe is speaking. Every new detection technology expands our senses. Gravitational waves extend our hearing. Neutrinos extend our touch. Radio waves extend our vision. Together, they reveal a cosmos alive with motion and vibration. The hydrogen line surveys show filaments stretching from Hydra Centaurus to Shapley, like strings connecting one note to another. X-rays reveal the shimmering heat of colliding clusters, where galaxies orbit within million-degree plasma. And gravitational waves will one day let us hear the collisions that shape those same clusters. The universe, it turns out, is not silent. It hums. It vibrates. It leaves traces of its own rhythm everywhere in the CMB's temperature ripples, in the 21 cm hiss of hydrogen, in the low, patient murmur of merging black holes. Each of these echoes adds another layer to our understanding of the Great Attractor and its place in the cosmic web. The more we listen, the clearer the harmony becomes. A universe that records itself. One of the most profound realizations of modern cosmology is that the universe contains its own history written into the radiation and particles that still fill space. Every process leaves a signature, a gravitational wave, a neutrino flux, a spectral line. Together, they form a complete archive of cosmic evolution, encoded in the very medium of existence. The Great Attractor is part of that archive. The galaxies falling into its core carry the fingerprints of ancient mergers. The X-ray gas tells of violent collisions, and the gravitational waves, yet to be detected, will one day play the soundtrack of its formation. In that sense, the Great Attractor is not only an object, it's a recorder of time. Every ripple, every particle, Every faint signal that escapes from it is another syllable in the cosmic autobiography, seeing with all senses. For much of history, we've been like listeners hearing only one note of a symphony. Now, with these new tools, we are finally hearing the chords, the harmony of the invisible. Soon, gravitational wave observatories in space, vast neutrino detectors buried under Antarctic ice, and radio arrays stretching across continents will operate as one integrated instrument. Together, they will map not only what we see, but what we can feel and hear from the depths of the cosmos. In that coming era, the Great Attractor will no longer be a shadowed mystery. It will be a resonant center in the universal song, its gravity, radiation, and motion woven into a tapestry of measurable echoes. We will not just observe the universe, we will listen to it live. The symphony expands. Each signal we uncover expands the symphony begun in gravity. The photons of light, the particles of matter, and the ripples of space-time all play together, spanning frequencies from trillionths of a second to billions of years. The universe has always been talking. It has always been music. We simply needed to build the instruments to hear it. Threads of darkness. If you could strip the universe of light, erase the stars, the galaxies, and every photon ever emitted, you'd find that something remains. It wouldn't glow, but it would still exist. A vast, interconnected skeleton woven through space. This is the dark matter web, the hidden architecture that gives the cosmos its shape. The Great Attractor is one of the densest nodes in this invisible network. Its gravitational power, enormous as it seems, is only the visible crest of a much deeper structure extending far beyond our view. Every galaxy cluster, filament, and void in our observable universe is part of this same web, a three-dimensional tapestry composed mostly of matter that cannot be seen, but whose influence is everywhere. It is not hyperbole to say that the Great Attractor is its dark matter halo, and that the visible galaxies we see within it are simply the luminous dust caught in its depths. The invisible framework. The concept of dark matter arose in the 1930s, when Fritz Zwicky noticed that galaxies in the Coma cluster moved too fast to be held together by visible stars alone. Decades later, Vera Rubin's measurements of galaxy rotation curves confirmed it. Stars in spiral galaxies rotated with nearly constant speed at all radii, implying the presence of unseen mass far beyond the visible disk. By the late 20th century, this missing mass was recognized as the primary component of cosmic structure. Observations of gravitational lensing, cluster dynamics, and the cosmic microwave background all pointed to the same conclusion. Roughly 85% of the matter in the universe is dark. Simulations like the Millennium and Bolshoi-Planck projects revealed what that means on a cosmic scale. In those virtual universes, dark matter condenses first, forming filaments and nodes long before stars appear. Gas and dust fall into those gravitational wells, forming the galaxies and clusters we see today. Without dark matter, there would be no Great Attractor, no Laniakea, no Shapley concentration, no cosmic web at all. Filaments, the universe's highways. Between clusters, like Norma, Centaurus, and Shapley, stretch enormous dark matter filaments, bridges of invisible mass connecting the densest regions. Each filament is hundreds of millions of light years long and tens of millions wide, containing not only dark matter, but also diffuse gas, galaxies, and magnetic fields. Recent observations using the Planck satellite's polarization maps and the LOFAR radio telescope have revealed glimpses of these threads. They emit faint radio signals from electrons spiraling along magnetic field lines like filaments of cosmic lightning threading the void. These filaments aren't static. Matter flows along them, drawn by gravity toward the nearest cluster or supercluster. In simulations, galaxies travel these filaments like cars along invisible highways, slowly converging on nodes like the Great Attractor. The flows that define Laniakea are the visible expression of these dark highways beneath. The magnetic web. Wherever there is motion, there is magnetism. As gas and plasma fall along dark matter filaments, they generate weak but pervasive magnetic fields, stretching over megaparsecs. In 2021, astronomers using LOFAR, the low-frequency array in Europe, detected diffuse radio emission between clusters Abell 0399 and Abell 0401, revealing a 10 million light-year magnetic bridge connecting them. This discovery confirmed what simulations had long predicted, that filaments in the cosmic web are magnetized. The magnetic fields are faint, on the order of 0.1 microgauss, about a millionth the strength of Earth's field, but they trace the flows of gas and cosmic rays across the universe. These fields may even influence how galaxies spin, align, and merge within structures like the Great Attractor. Some cosmologists suspect that magnetism could play a role in shaping the morphology of superclusters themselves, adding a subtle electromagnetic tension to gravity's pull, an unseen harmony woven into the web. The warm-hot intergalactic medium, WIM. Between the galaxies that populate these filaments lies a ghostly plasma known as the warm-hot intergalactic medium, WIM. It consists of tenuous gas at temperatures between 10 to the power of 5 and 10 to the power of 7 Kelvin, shock-heated as matter falls into the filaments. The WIM is hard to detect, but X-ray and ultraviolet observations from missions like Chandra, XMM Newton, and eROSITA have begun to map it. In 2020, astronomers found clear evidence of the WIM linking the Abell 222 and Abell 223 clusters, a filament stretching 10 million light-years. The WIM likely contains a large fraction of the universe's missing baryons, the ordinary matter not accounted for in galaxies or hot cluster gas. If the Great Attractor's filaments are filled with him, they may hold much of the visible universe's unobserved matter that literally connects us to Shapley and beyond. These streams of hot gas are the veins of the cosmic body, carrying the nutrients of star formation from one cluster to another. The texture of darkness. Although dark matter itself is invisible, its gravitational influence sculpts everything around it. Using weak gravitational lensing, astronomers can measure how the light from distant galaxies is subtly distorted by the invisible mass in the foreground. Large surveys such as the Dark Energy Survey, DES, and Keed's Kilo Degree Survey have mapped these distortions over thousands of square degrees, revealing the dark matter distribution in the nearby universe. What they found confirms the predictions. The dark matter forms an interconnected web of filaments and nodes, just as simulations suggested. In regions corresponding to the Great Attractor, lensing maps show significant mass concentrations consistent with overlapping halos from the Norma and Centaurus clusters, possibly connected to the larger Hydra Centaurus filament. Even through the zone of avoidance, the gravitational fingerprints of these masses can be inferred indirectly from the motion of background galaxies. The texture of darkness, it seems, is not smooth but granular, a pattern of nested structures, fractal-like, repeating across scales. The particle question. But what is dark matter really? For decades, physicists have searched for its fundamental particle, with candidates ranging from WIMPs, weakly interacting massive particles, to axions, sterile neutrinos, and ultralight scalar fields. Despite decades of searches in deep underground detectors and particle accelerators, no direct detection has been made. Yet astronomical evidence remains overwhelming. Every simulation that includes dark matter reproduces the cosmic web. Those that omit it fail completely. Whether it is a particle, a field, or a modification of gravity itself, something unseen provides the scaffolding of the universe. The Great Attractor, with its immense gravitational signature, stands as a natural laboratory for this mystery. By measuring how galaxies move within its basin and how X-rays trace the hot gas in its clusters, astronomers can test competing models of dark matter's behavior, cold, warm, or self-interacting. The answers may one day come not from particle physics, but from the motions of galaxies 500 million light-years away. Tension between dark and visible. What makes the Great Attractor fascinating is the mismatch between what we see and what we feel. Visibly, it contains only a few known clusters: Norma, Centaurus, Parvo, and perhaps others obscured by the Milky Way. But its gravitational influence suggests a total mass equivalent to tens of thousands of Milky Way galaxies. This means that most of its mass is invisible, even to our most sensitive instruments. The region's gravitational potential is smoother and more extended than can be explained by luminous matter alone. One possible explanation is that the Great Attractor is not a single dense clump, but a thick convergence of dark matter filaments, a place where several cosmic strands meet, amplifying the gravitational field. This interpretation aligns with large-scale flow models, where the Great Attractor marks the junction between multiple streams leading into the Shapley concentration. In essence, it may be less a thing than a knot in the fabric of the universe. Cosmic strings and ancient tension. On even grander scales, some physicists speculate that dark matter might not be particulate at all, but a remnant of cosmic strings, one-dimensional defects in space-time left over from the early universe's symmetry breaking. These hypothetical strings, predicted by certain grand unified theories, could stretch across billions of light-years, with enormous tension pulling at the universe's fabric. Though no direct evidence exists, the large-scale alignment of structures like the Great Attractor and Shapley sometimes inspires comparisons to such ancient filaments of energy. Even if cosmic strings are never found, the idea captures a deeper truth. The universe remembers its own formation. The same primordial fluctuations that seeded the CMB's patterns are now stretched into the vast filaments that bind superclusters together. Each dark matter thread is a fossilized vibration of the early cosmos, magnetism between worlds. In the voids between clusters, the faint magnetic fields connecting them may also play a role in shaping cosmic motion. Observations from Planck have detected polarized microwave emission tracing the alignment of dust grains along intergalactic magnetic lines, suggesting that even the empty regions of space are not truly empty. These magnetic fields could help guide charged particles and cosmic rays through the universe, forming a bridge of energy between galaxies. They might even influence how galaxies orient themselves relative to their parent filaments, a subtle alignment that cosmologists have only recently begun to measure. It's as though the universe's invisible threads not only hold matter together, but communicate between its parts, transmitting both gravity and magnetism across unimaginable distances. The loom of creation. When all these components, dark matter, gas, plasma, and magnetic fields interact, they weave the cosmic tapestry. The Great Attractor sits at one of its densest intersections, where multiple filaments meet and twist together, forming a gravitational vortex that shapes everything around it. From a distance, you might imagine this as a cosmic loom, filaments converging, knots forming, threads stretching into the distance. The galaxies are the beads strung along those threads, luminous markers of the underlying pattern. And though we cannot see the loom itself, we can trace its pattern through motion. Every peculiar velocity, every gravitational lensing event, every filament of gas or magnetism we detect adds another line to the blueprint of the universe's hidden structure. Darkness as structure, not void. To call it dark matter may be misleading. The word suggests emptiness or absence, but the reality is the opposite. Darkness is not a lack. It is the foundation, the scaffold, upon which all luminous things are built. In that sense, the Great Attractor's darkness is creative. It doesn't destroy light. It gives light a place to gather. It defines the architecture of reality, ensuring that stars have somewhere to form, galaxies somewhere to orbit, and superclusters somewhere to flow. Without darkness, there would be no form. Without the invisible, there would be no visible. The hidden fabric. As our instruments improve, the dark matter web becomes more tangible. Weak lensing maps, X-ray observations, and radio surveys increasingly reveal that the universe's true structure is not random, but woven each filament part of a continuous fabric stretching from one end of the observable universe to the other. And somewhere near its center, deep within that web, lies the Great Attractor, an immense, invisible knot in the tapestry of space-time. Its gravity is not isolated, but shared. Its darkness, not absence, but connection. In every direction, filaments lead away from it, like threads in a cosmic cloth, linking us to everything else that exists. The tides of time. The universe is not static. Everything that exists, galaxies, clusters, superclusters, is adrift in an ocean that changes shape as it expands. The Great Attractor, magnificent as it is part of this flow. Its gravitational pull binds thousands of galaxies, but beyond its reach, the cosmic tide continues to rise, driven by a mysterious force that no mass can overcome. The story of the Great Attractor is not just about where we are being pulled, but about how long that pull will last. For gravity itself, like everything in the cosmos, faces an adversary it cannot yet defeat. Dark energy, the expanding stage. When Edwin Hubble measured the redshifts of galaxies in 1929, he discovered that the universe was expanding. Space itself stretches, carrying galaxies away from each other like raisins in rising dough. In that expanding framework, the Great Attractor is a local distortion, a place where gravity is strong enough to resist the stretch, binding galaxies together despite the universe's growth. But that expansion isn't constant. In 1998, observations of distant Type Ia supernovae revealed something startling. The expansion is accelerating. Instead of slowing down under the pull of gravity, the universe is speeding up, driven by a repulsive energy embedded in space-time itself. This dark energy dominates the cosmos. According to the latest Planck mission data, dark energy constitutes 68.5% of the total energy density of the universe, dwarfing both dark matter and ordinary matter combined. As it continues to accelerate, the space between distant superclusters grows faster than gravity can pull them together. Eventually, structures like the Great Attractor will become isolated islands in an ever-widening cosmic sea. The boundaries of attraction. Today, the Great Attractor's influence extends across roughly 250 million light-years, drawing in galaxies at velocities up to 600 kilometers per second. The Shapley concentration, farther beyond, exerts its own pull across even greater distances. For now, gravity wins locally. Within these superclusters, galaxies remain gravitationally bound, but cosmic acceleration has a scale beyond which no structure can coalesce. That scale is known as the turnaround radius, the distance at which expansion balances gravitational attraction. For the Great Attractor's mass, around 10 to the power of 16, 10 to the power of 17 solar masses, that radius is on the order of 400 million light-years. Beyond it, galaxies are swept away by the expansion of the universe faster than gravity can reel them back in. As the universe ages, that boundary moves inward. Gravity's domain shrinks. The Great Attractor's reach will one day end at its own edges, surrounded by galaxies it can no longer pull closer. The tides of time are rising, and the islands of matter are beginning to stand alone. A timeline of cosmic isolation. If we could watch the future unfold, here is what we'd see 10 billion years from now. The Milky Way and Andromeda will have merged into a single elliptical galaxy. Together, they will form the heart of a vast remnant cluster orbiting within what remains of the Laniakea supercluster. The Great Attractor will still hold hundreds of thousands of galaxies, but beyond its borders, the space between superclusters will have expanded dramatically. The Shapley concentration will be slipping away, its light fading as cosmic redshift stretches it beyond visible wavelengths. 100 billion years from now, the acceleration will have isolated each supercluster completely. The Great Attractor and its neighbours will exist as an island universe, gravitationally bound and separated from all others. Beyond its boundaries, expansion will carry every distant galaxy away faster than light can travel. From any vantage point inside, the universe will appear to end at the edge of the local supercluster. The cosmic web will dissolve into a network of disconnected nodes, each drifting alone in the dark, 1 trillion years from now. Even within those islands, change will continue. Galaxies will merge, stars will exhaust their fuel, and new star formation will dwindle. The Great Attractor's brilliant clusters will fade to red, then infrared, then invisible as the last generations of stars burn out. The universe will grow quieter, colder, and emptier. The tides will have turned for good. The dimming web. The cosmic web that now connects superclusters will not endure forever. As the universe expands, the filaments of dark matter and gas that link regions like Hydra Centaurus and Shapley will stretch and thin. The warm-hot intergalactic medium, once a network of glowing plasma, will cool below the threshold of detectability. The magnetic bridges that span millions of light-years will dissipate. Filaments that once guided galaxies along invisible highways will snap, leaving the Great Attractor marooned in a vast cosmic void. To any future astronomer living within that distant epoch, the universe will appear static and small. They will see only the galaxies bound to their own supercluster. The Great Attractor will seem eternal, unchanging, its motion through space no longer measurable because everything beyond it will have vanished beyond the cosmic horizon. In that distant time, the Great Attractor will still be there, but the story of its discovery will be impossible to repeat. The clues we use today, the cosmic microwave background, the recession of galaxies, the flow toward Shapley, will all be erased by expansion. The age of black holes. As the last stars fade, the universe will enter what physicists call the degenerate era. Stellar remnants, white dwarfs, neutron stars, and black holes will dominate. Gravity will continue to pull these remnants together, forming larger black holes that slowly merge over unimaginable timescales. In the heart of the Great Attractor, supermassive black holes from clusters like Norma and Centaurus may eventually coalesce into a single object, perhaps containing the mass of tens of trillions of suns. Its event horizon would span light years, a dark monument at the center of a darkening universe. Occasional mergers between these colossal black holes will still send gravitational waves rippling through space-time, soft, low-frequency murmurs, detectable only by the most sensitive instruments. These will be the final echoes of the Great Attractor's symphony. Even after everything else fades, gravity will continue to make music. Heat death and the fading pull. After trillions of years, even black holes will not last forever. According to Stephen Hawking's theory of quantum evaporation, they will slowly lose mass by emitting radiation, a process so slow that it takes 10 to the power of 66 years for a stellar mass black hole to vanish. The supermassive black holes of the Great Attractor will survive for far longer, on the order of 10 to the power of 100 years. When they finally evaporate, they will release the last whispers of the Great Attractor's gravitational energy into the surrounding void. The structure that once dominated our cosmic neighborhood will dissolve into a thin haze of particles, leaving behind only the faint curvature of space-time it once shaped. At that point, the universe will have reached thermal equilibrium, everywhere the same, everywhere silent. No new stars will form, no new structures will arise. The gravitational tide will have gone out forever. The arrow of time, the Great Attractor's fate, mirrors the universe's own arrow of time. It was born from collapse, the local gathering of matter from an expanding medium, and it will die through dispersal, as the same expansion pulls everything apart. Entropy, the measure of disorder, increases inexorably. Every collision, every merger, every burst of starlight converts gravitational potential into heat, and heat into the uniform hum of the cosmic background. The grand patterns of today, the filaments, clusters, and flows, will one day smooth out into a featureless cosmos. But in that slow descent, there is beauty. The universe is not racing toward death, it is completing its composition. Every fall, every merger, every glowing epoch of structure is a note in a cosmic requiem, one that began with the first density fluctuations and will end in perfect stillness. Our place in the timeline. Right now, we stand at a rare moment in cosmic history, a balance point between the past and the future, when both gravity and expansion shape the universe in equal measure. We can still see the CMB from the beginning of time. We can still watch galaxies recede at relativistic speeds. We can still measure the gravitational flow toward the Great Attractor and beyond. In the deep future, none of this will be possible. It's as though we live in the universe's most visible era, an epoch when light, gravity, and expansion are all simultaneously accessible to perception. To be alive now is to stand at the crest of cosmic intelligibility when the universe is large enough to explore, yet young enough to remember its own origin. In a sense, the Great Attractor doesn't just pull on galaxies, it pulls on our understanding. It gives us context, direction, and the ability to see the unfolding of time itself. Gravity's last victory. Even as dark energy drives the universe apart, gravity will never vanish. It will continue to bind what it can, stars to galaxies, galaxies to clusters, and clusters, into the final, fading superstructures that will persist long after the rest of the cosmos slips away. The Great Attractor's core may survive a gravitational island in a limitless ocean of darkness, holding its remaining galaxies close as the universe expands around it. Those galaxies will continue to orbit for trillions of years, long after all external motion has ceased. It will be, in its way, a triumph of gravity's persistence, a final chord resonating across eternity. The stillness beyond motion. If we could leap forward to that far future, to the last age of stars, we might look back and see how transient all of this was. The filaments, the flows, the superclusters, all temporary patterns in an evolving sea. But even in stillness, the memory of motion remains. The curvature of space-time retains the imprint of everything that ever moved through it. The paths of galaxies, the ripples of gravitational waves, the expansion of the voids, all leave their traces in the geometry of the cosmos. The universe, even when it sleeps, will remember its song, the tide that carries us. We, the observers, are part of this story too. The same physics that will someday silence the stars also governs the atoms in our bodies. The same expansion that stretches galaxies apart carries the molecules of our planet through space. When we look toward the Centaurus constellation and imagine the Great Attractor pulling us in, we are also watching the future, an unfolding that includes not just galaxies, but the very concept of motion itself. Time and gravity, two faces of the same coin, carry us together down the same river. Our place in the current. You are moving. Right now, as you read these words, your planet spins eastward at more than 1,600 kilometers per hour. The Earth itself orbits the Sun at 30 kilometers per second. The Sun drifts through the Milky Way at 220 kilometers per second, pulled by the gravity of billions of stars. But those motions are just the beginning. The Milky Way, together with its companion galaxies, races toward a distant region of space, a gravitational abyss hidden behind the Milky Way's glare at 600 kilometers per second. We call it the Great Attractor, but that name barely captures what it is. It is not a single object. It is not a black hole. It is a convergence, a deep gravitational basin where filaments of the cosmic web meet. Our galaxy is one of countless travelers caught in its pull, drifting through the slow, endless river of space-time. You are not standing still. You are flowing through the universe, the river beneath us. Imagine space not as emptiness, but as a vast current, invisible, unending, patient. Galaxies drift through it the way leaves drift down a slow-moving river, following channels carved by gravity over billions of years. Our local group floats within this current, which flows through the Laniakea supercluster toward the basin of the Great Attractor. Beyond that, the current continues toward the Shapley concentration, hundreds of millions of light-years farther downstream. It is a hierarchy of motion. The Earth circles the Sunday. The Sun circles the Milky Way. The Milky Way circles the center of Laniakea. And all of Laniakea slides toward Shapley, an ocean current made of galaxies, dark matter, and time. The word current feels poetic, but it's also literal. Galaxies are not just falling, they are flowing through a gravitational field shaped by billions of invisible masses. The paths we trace are the fingerprints of space-time itself, sculpted by density and curvature. In a way, we are passengers on an ancient voyage that began before the Milky Way even existed, the human horizon. For all its vastness, the story of the Great Attractor is also a story about seeing. Every advance, every redshift measurement, every X-ray map, every infrared survey was an act of extending our horizon. From Earth, we see only about 46 billion light-years in any direction, the limit set by the age of the universe and the speed of light. But that boundary is not static. Every year, light from more distant galaxies reaches us, expanding the map we can draw. The Great Attractor lies well within that visible sphere, a region we can detect but not yet fully resolve. To explore it, we've learned to see without sight, to use gravitational lensing, radio waves, and motion itself as guides. In doing so, we've also extended the meaning of observation. We no longer define seeing by light alone. We see by listening to space-time. We see by tracking motion. We see by recognizing patterns in the flow of galaxies, patterns that reveal the architecture of the invisible. The Great Attractor reminds us that knowledge itself is a form of motion, the movement of the mind toward deeper gravity wells of understanding, a snapshot in a moving universe. Everything we know, from the Milky Way's shape to the cosmic microwave background, is a snapshot of motion. We live inside a frame that moves. The sky we see each night is not static, but stretched and redshifted by the universe's expansion, bent by the gravity of structures between us and the edge of time. Even the Great Attractor, which seems like an anchor in the galactic flow, is moving, drawn toward Shapley, which is drawn toward something deeper still. Everywhere in the cosmos, motion is relative. There is no center, there is no still point. Every object defines its own frame of rest, and each is carried by the same invisible tide. And yet, in that motion, we find order. Galaxies move coherently, bound by common flows. Superclusters rotate and fall together. The universe is not chaos, it is choreography. Every trajectory is part of a pattern, every pattern part of the web. To look up at the night sky is to glimpse that pattern midstream, a frozen instant in a current that has no beginning and no end, the scale of belonging. When we map the Great Attractor and Laniakea, it's easy to feel small. The numbers themselves dwarf imagination. Millions of light years, trillions of suns, velocities measured in hundreds of kilometers per second. But those same numbers also connect us. We are not outside the cosmos, looking in. We are within it, made from the same matter that flows through its filaments. Every atom in your body, every carbon, nitrogen, and iron atom was forged in ancient stars that drifted along those same filaments. When those stars exploded, they seeded the gas that would one day form new generations of stars, new planets, and eventually, life. You are, in a very real sense, the universe becoming aware of its own structure. The Great Attractor does not just pull galaxies, it pulls our curiosity, our need to understand why we move and what lies ahead. That gravitational curiosity is part of what makes us human, the observer's paradox. From our position inside Laniakea, we observe the universe as if from within a whirlpool. Everything seems to move relative to us, yet we, too, are part of that motion. In physics, there is no preferred vantage point, no cosmic center, only reference frames. And yet, emotionally, we crave one. The Great Attractor satisfies that craving in a strange way. It gives us direction without giving us center. It offers a destination without an endpoint. The awareness that we are falling, not metaphorically, but literally, through space-time, changes how we see ourselves. The Earth is not a static world beneath a fixed sky. It is a vessel, adrift in the gravitational ocean. Every sunrise, every orbit, every year is part of a much larger descent, a journey shared by billions of galaxies through the same invisible field, the light that carries us. One of the most poetic aspects of this realization is that the light we see from distant galaxies carries not just their images, but also the record of our own motion. The cosmic microwave background shows a dipole pattern, a slightly warmer glow in the direction we're moving, and a cooler one behind us. That difference, only a few thousandths of a degree, encodes our velocity through space. It's humbling to think that the universe itself reveals our motion in its afterglow. The cosmos doesn't just contain us, it registers us. Our movement, small as it is, leaves a measurable imprint on the oldest light in existence. Even the Great Attractors pull that 600 kilometers per second vector through Centaurus and Norma is written into the background of creation. The universe keeps score, quietly, in the geometry of space-time, the continuity of discovery. For astronomers, the Great Attractor is both a mystery solved and a question reopened. It led to the discovery of Laniakea, the redefinition of superclusters, and a revolution in how we map motion through the universe. But it also pointed the way to larger structures. Shapley, the the dipole repeller, and the still unknown attractors that may lie beyond the edge of our surveys. Science, like gravity, has no final resting place. Each discovery deepens the field that pulls us onward. The zone of avoidance that once hid the Great Attractor is now shrinking with every new infrared and radio observation. Tomorrow's telescopes, Euclid, SKA, LISA, and their successors, will continue to clear the fog. The Great Attractor began as a shadow on our maps. Now it is a mirror, showing us the relationship between motion, perception, and persistence. It reminds us that even when the path is obscured, the pull toward knowledge never ceases. The intimate vastness. There is something deeply paradoxical about cosmic scale. The farther out we look, the more we understand what it means to be local. The same laws that shape galaxies also govern the orbit of a moon, the fall of a leaf, the pull of a heartbeat toward the ground. The Great Attractor is unimaginably far away, yet its influence reaches us here, in the present moment. Its gravity passes through the Milky Way, through the Sun, through you. In its field, we are participants, not spectators. Every atom in your body is caught in that same movement. You are not separate from the flow, you are the flow, condensed for a moment into consciousness, the quiet center of motion. If you could stop the universe and stand outside it, impossible as that is, you'd find that motion never ends. Every particle, every photon, every galaxy is moving relative to something else. There is no absolute stillness, no fixed point to hold on to. And yet, within that endless motion, there is a kind of peace. Motion implies connection. To move is to belong. The Great Attractor doesn't threaten us with chaos. It enfolds us in a pattern too vast to perceive all at once. It's not a center we orbit, but a current we share. Perhaps that's the real meaning of the Great Attractor. Not a place, but a relationship between everything that moves. What remains. In the end, the Great Attractor will fade from view, just as all things will. The accelerating expansion of the universe will one day carry even its light beyond our horizon. But that doesn't erase its story. Its influence will persist in the paths of galaxies, in the curvature of space-time, and in the echoes of our measurements. Our descendants, if they survive into that far future, may live in a cosmos where only their local galaxies remain visible. Yet buried in the data of their ancestors will be proof that they once belonged to something vast, a cosmic archipelago, linked by gravity across hundreds of millions of light years. And they will know that, once, their galaxy was part of a current that flowed toward a great invisible valley, and that through that valley, all things were connected. The mirror of motion. When we study the Great Attractor, we're not just learning about space, we're learning about ourselves. We are pattern-seeking creatures in a patterned universe. The same physics that governs the Great Attractor governs our neurons, our tides, our orbit around the Sunday. To see that continuity is to feel awe not just for what is vast, but for what is near. The universe does not divide the small from the large, or the human from the cosmic. It is one continuum of matter and motion, from quarks to clusters, from the whisper of a falling leaf to the drift of entire galaxies. The Great Attractor's gravity is, in a sense, the same gravity that lets you stand on the Earth. The difference is only in scale, not in kind, the current within. If you could translate our motion through the universe into sound, it would be a deep, slow hum, a note billions of years long. You could call it the heartbeat of gravity. And it would not just be the Milky Way's song, but the resonance of everything from atoms to clusters vibrating together across space-time. In that hum, there is no separation between the observer and the observed. We are the sound. We are the vibration. We are the motion itself. To know the Great Attractor is to know that you, too, are moving not metaphorically, but physically, through the same currents that bind the galaxies. You are part of the long descent of matter through time, the slow unfolding of the universe's hidden geometry. And maybe that's the truest kind of stillness. Not the absence of motion, but the awareness of it. Epilogue. The pull of wonder. The Great Attractor will always remain, in some way, beyond our reach. Partly hidden, partly inferred, always larger than what we can see. But that is what gives it power. It represents the horizon of our understanding, the point toward which curiosity itself is drawn. In every age, humans have looked upward and wondered what moves the stars. Now we know. They move because space-time bends, because gravity binds, because the universe is alive with motion. And within that motion, we have found meaning. We may never arrive at the Great Attractor, but its pull will always be with us, not just as gravity, but as wonder. The same invisible force that draws galaxies together draws us toward knowledge, toward exploration, toward awe. And so, as our galaxy continues its long drift through the darkness, we can take comfort in knowing that we are not lost. We are following the current, the same current that has guided everything since the dawn of time.